For those who have joined late, there is a link in chat box. You have to click on that, and even the event code is shared. Copy paste the event code here, click on enroll, then go to this course, CUDA Python, and click on first chapter, Introduction to CUDA Python with Numba, and click on start button. Your cloud instance will be ready in 5 minutes. Okay, so we're good to go now. So in previous course, we have seen fundamentals of CUDA programming with C, C++. Now we'll see the CUDA programming, how we can perform this CUDA programming in Python language. Okay, because we have both set of audience here from C, C++ background and Python background. And again, even though you're not much familiar with Python, but still you will be able to understand the CUDA concept, right? You don't have to be very proficient in Python programming language. Just like from previous certification, you should be available. You should be aware of how to write Python function, right? How to pass the parameters, about the loops, right? So these are the basic things required only, and few advanced things are there. But again, you don't have to go into details of those topics like decorators, etc. Okay, so you just need to use it. You don't have to worry about how it internally works. Now, here I have started the first chapter. I can click on the launch button now in order to open this chapter. And note that just like previous certification, here also we have 3 chapters. Only difference is in previous certification, there was only one assessment, right? But in this certification, you have 3 assessments and one in each chapter. Okay. The assessments are very simple because now you are familiar with CUDA programming. So you'll be able to do that as assignments very quickly. Okay. And we will try to complete these assignments during the live session itself. Okay. So now open this chapter 1, Introduction to CUDA Python with Numba. And what we are going to see throughout this course is first we'll see CUDA Python with Numba, that is a compiler available, and you will enjoy this compiler because it performs all the parallelization automatically on behalf of you, right? So that is an intelligent compiler is there on behalf of you. It will perform the parallelization optimization on both CPU and GPU. You just need to tell that you want to make this particular section or function in program parallel. That's it. And it will take care of everything, writing CUDA function, deciding the number of threads and blocks, everything internally, how to transfer the data, everything is taken care. In second chapter, we'll see how to write custom CUDA kernel the way we have written in the previous CUDA C, C++. Okay. So the same thing is repeated here. So chapter 2 is quite easy because you already aware with the CUDA programming. So you'll be able to complete the course immediately. And for chapter number 3, few advanced topics are there that were not even covered in the CUDA C, C++, right? So deliberately, I am taking those topics in this certification because it will be redundant if I take both certifications. Okay. Now, these are the 3 chapters we are going to see, and we will see the first chapter is introduction to Numba. Okay, but before that, let me ask few questions. Whether Python is compiler-based programming language or interpreter-based?
Interpreter.
Okay, great. And can you tell me what's the difference between compiler and interpreter?
Interpreter does single line work, whereas compiler just translates into machine language all at once.
Exactly, right. Absolutely correct. So Python is an interpreter-based language which check semantic and syntax of program line by line, right? And here I am saying that we are going to use a Numba compiler in Python. Okay, right? Quite a contradictory statement here. We are going to use Numba compiler in Python program. Okay, so what's the purpose of this Numba? It compiles Python functions for CPU. It compiles Python functions for GPU, right? It accelerates some Python NumPy functions, right? And also it GPU accelerate vectorized functions, right? So we'll see it also optimize the data transfer. So we will see all these things in this particular chapter, how this Numba compiler is going to help us. Note that here we are not going to explore CUDA thread hierarchy, uh, block dimension, grid dimension, etc. Here it is completely automated parallelism, right? For example, you are telling there is an intelligent compiler is available for you, and you are telling compiler that okay, this is the function I just want to optimize and parallelize. You do it by yourself, and compiler is intelligent enough which will automatically detects whether you have CPU or GPU in your system, right? Based on the CPU or GPU architecture, it will try to optimize the code, parallelize it. If it is on GPU, it will transfer the data automatically, right, to and fro on the GPU. Everything is taken care by the compiler, and you will get the performance, right? So this is one of the way you can achieve code optimization using Numba. Okay, so what is Numba here? It is a function compiler, right? So when you say compiler, that means all lines in your code are supposed to be compiled, right? Now, it is not a complete source code compiler. It is simply a function compiler. That means it takes the function body and it is going to compile the entire function body at once, right? So remaining part of your Python code will be again interpreter based only, right? Only the function that you want to optimize by means of Numba compiler, only that particular function we are going to compile using this Numba. Okay, so that is first thing. It is type specializing. Okay, we'll see the type specializing in detail later. It is just-in-time compiler and it is numerically focused. So what do you mean by numerically focused here? It is right now supporting only the data types like integer, float, complex, where we perform the numerical computations, right? Addition, division, subtraction, multiplication, and other trigonometry or logarithmic operations that we perform normally on the data, right? So that those operations are of type numerical, and data type is called as numerical data type. And it is having very limited support for the data type like string, right? So because we cannot perform the operations like addition, division, multiplication on string, so different set of operations are there, and as of now there is a limited support available for this string data types, right? So this is Numba. We'll see with hands-on how this Numba is going to help us and how it is going to be function compiler, right? Now these are the requirements if you want to use Numba, but this is only if you want to install and use this Numba compiler in your local system. And these are some requirements are there. So I'll skip that requirements because we have already pre-installed everything available in the cloud platform. So it is just for your information. If in future you want to install this Numba. So these are the minimum requirements you have to satisfy. Okay. Now, one question you might ask that, okay, so we have this Python based CUDA programming. We have C, C++ based CUDA programming is there, right? So which one to choose? Okay. So actually there are three options are there if you want to write a CUDA program. Okay, in C++, and Python. Apart from that, you can use other programming languages also. But these are the programming languages which widely and supported for this CUDA programming. And here you have three choices: CUDA C++, PyCUDA, and Numba. Okay, so out of which you are already familiar with this CUDA C++, right? So that is the most common and which gives you maximum performance, CUDA C++, right? And which is having, where you can go and optimize by going at very low level in case of CUDA C++, because C and C++ programming languages are much closer to the hardware, right? So here you have lot of freedom, flexibility to optimize CUDA programs here in C++ platform. Unlike if let's say your application is very performance important, right? Then it is recommended to go and develop your application using C++ only, right? For example, you want to predict what is weather of tomorrow, then the code is written in C++ because uh, the code itself is contains millions of lines, and which takes lot of time, right? So lot of computations you have to perform just to tell whether there is going to be rain tomorrow or not, right? So here the time is critical. Same way in the share market where you want to purchase or sell the stock, uh, and that decision you have to take at very fraction of second, right? So where performance is very, very critical, then in that sort of applications, CUDA C++ is recommended. But let's say you have one application that is already developed in Python, right? And it is not that much performance critical, right? So if it is taking, let's say, 1 day time to execute that program, and if you bring it down to, let's say, half day or 2-3 hours, then it is recommended that go with the CUDA APIs, C++ APIs used in CUDA Python program, right? So that means just like in Python, you use C++ APIs to execute some portion of the C++ program. Same way, there are some APIs that help you to use this CUDA C++ program in the Python source code. Okay, so this way you don't have to modify your Python existing Python program, right? So with a few additions of CUDA C++, you will enjoy the performance improvement. Okay, and the final option is Numba, where it is potentially the less performant than both, right? C++ and PyCUDA. The reason is here it is totally depend on the compiler, Numba compiler, and its way of optimizing the program. Okay, so though I'm saying it is less performant, that doesn't mean that it is not giving performance at all. It is gives massive acceleration, right? But you, as a programmer, you don't have to do much modifications in the code, right? So with minimal changes in the code, you will be able to enjoy few many-fold performance. Okay, and good thing about this Numba, it also optimizes the code on CPU side, right? On CPU side also you are having multiple cores present, but the CUDA C++ is not going to help you to optimize code on CPU side. It optimizes or parallelize code only on GPU side. But this Numba compiler asks you where you want to optimize your code. If your target device is the CPU, so it will consider the underlying device architecture, count its number of cores present, and automatically it is going to parallelize and optimize the code for the CPU side. The same way, if you say that I want to optimize and parallelize my code on the GPU side, then it is going to do the same thing for the GPU, right? So you will get to know in few minutes that just by writing a single line of code, you will be able to get the performance improvement in the code. Okay, just I'm repeating the statement. Just by adding one line in your function, you will be able to improve the performance of your code, right? And that line is nothing but just to give instruction that, okay, this is the function I want Numba to optimize it. That's it. Okay. So we'll try to understand this automated parallelism by using this by Numba compiler. And first we will try to compile the function for the CPU side. Okay, fine. So just quick update. If the students who have joined late, there is a link in chat box. You have to click on that link. You will get diverted to this page, and the event code is shared in the chat box. Use that event code here and click on enroll. Then click on the first chapter here, Introduction to CUDA Python with Numba, and then click on start button, right? Once launch option is available, then click on launch button. The same steps you have to follow just like we followed in the previous certification. Okay. The event code is also available in the chat box. Let me know whether you are able to see the event code or not in the chat. If not, let me share it one more time. Okay, here it is, the event code. So you can use that event code. Okay, so the first step, what we are going to do, we will compile the CPU functions, right? So that means Python function, but we will use this Numba compiler to optimize it for the CPU side. Now, one disclaimer here, there are some mathematical functions we will be using throughout this certification, but you don't need to understand mathematics behind it. Okay, it is completely optional. Being programmer, we will simply observe the computations, how they are getting performed and in which order they are getting performed. That's it. Okay, we are not mathematic experts, so we don't want to explore and we don't want to invest our time in that. Rather, we just want to understand how I can take any Python function and parallelize it. That's it. Okay, so don't worry if you are not able to understand, for example, what is this hypod function is doing. It is doing some complex computation. What is its meaning? Don't try to investigate what its meaning. So just focus on the computations, right? Now, in Python, we have a function decorator concept, which improves the functionality of the given function. Okay, so if you want to explore that, you can click on this function decorator and see what you mean by that and how we can use it, that function decorator. But to be frank, we don't have to investigate in detail because we are just using the decorator to tell that you want to optimize it, how it is going to optimize, and internally how it is going to work. We don't want to understand, learn here, right? So we'll just trying to give the orders here. And the function decorator will be placed above this function definition, right? Now we want to use the Numba compiler. So first of all, we have to import Numba, right? From Numba, I'm going to import this JIT compiler, just-in-time compiler. Then the math package we are loading here. And then if you see, this is the hypod function, which is taking two arguments, X and Y, and is performing some computations and is returning some value, right? X into square root of 1 plus t square, that is the value it is returning. Okay, now how to optimize this function for CPU? We will use that JIT decorator on the function definition, and that's it. right? So this is how we give the order, and automatically now this JIT compiler understand that this is the function which needs to be optimized on CPU side, and automatically it performs internal optimizations, and we'll see how its performance gets improved. Okay, so this is the function I used the @JIT here, and now we will see where results are correct or not. So this is the hyport function that is optimized by JIT compiler. And let's say you don't want to, let's say, execute the optimized one. You want to execute the real one, which is not optimized by JIT. Then you use the same hyport function name, but here you use .py_func, right? So this way you will execute the original Python code, right? Not the one which is optimized by the JIT. So by default, if you call this hyport, it will execute the optimized one. And if you use .pyfunc, so it will use the default or the unoptimized one. Okay, so this is the difference between calling hyport and hyport.py function, right? So you see the parameters are same, only we are calling .pyfunc to tell that we are executing the original one. Just quick confirmation whether I'm clearly audible or not, because I'm getting here message that my network is not stable.
Yes,
Am I
sir.
clearly audible? Okay, thank you.
Sir, JIT will
Yes.
automatically optimize by itself. We don't have to
Yes.
do anything.
No, but we just need to tell that this function. Look, what I did here, there is already function hyport that is written. I just imported JIT and I mentioned his decorator, and automatically it is taken care. Fine. So in first chapter, you will enjoy this automated parallelism. Okay. Yeah. So this pyfunc, look, this is the hyport function. We used it. So when you execute it, by default, it will execute the optimized one, right? But let's say you don't want to execute the optimized one. You just need to execute just like there is no decorator, right? So default will be here executed if you call by this py_func. Okay, so that's the difference. So this is the optimized and this is unoptimized by JIT. Now let's see what's the performance difference between these two, right? So there is a time it magic function is there in Python. So it will give the time required to execute the code present in this cell. Okay, so we are calling hyport.pyfunc. So this one is unoptimized, right? So if I execute it, it will give me how much time it is required to execute the default hyport function without any optimization, right? It is taking 689 nanoseconds. Now we will execute the hyport, which one is optimized one. Okay, so if I execute this, now you will see the time required here for the optimized hyport function is okay, it is taking 193 nanoseconds, right? So if you don't use a Numba compiler, then it is taking 689 nanoseconds. And if you use Numba compiler, it is taking 193 nanoseconds, right? So now how to see the performance improvement? There is a term called as speed up. Okay, in parallel computing, we measure the start with the pen. Speed up. Okay, so in parallel computing, we measure the speed up, the how much time it is taken for the sequential program and how much time it takes to the parallel one. So here it took 689 nanoseconds and divided by here 193 nanoseconds, right? So approximately it is 3 times performance. So we measure or we say the performance improvement is 3x or 3 times. Right? So here we got the performance improvement 3 times. note that this is only on the CPU side only. We try to optimize code on the CPU side only. Okay, so that's why here we got the performance here 3 times, and this is called the speed up, that is a performance metric, right? So note this performance metric, we will use this performance metric very often in upcoming topics. Now, here we imported one, Yashwardhan, I'll answer to your question. Just hold on for a minute. So here we have tried to check the performance of a default hypod function, the optimized hypod function. Okay, and these function is user defined function. Now there is a function, similar function hypod in math library here. Okay, and if you see, if I execute this hypod function from math library and if I measure its time, now let's see how much time it takes. Okay, it is taking 131 nanoseconds, right? Which is even faster than the optimized Numba function. Okay, then you may say in math library, there is a hypod function which is not even optimized by the Numba, but still it is faster than this Numba compiler. How is it possible? Because I'm saying that just because use of Numba compiler, which will help you to improve the performance on CPU side, but there is another function present, same function present in math library, which is not being optimized by Numba, but still it is faster than Numba. Then what's the use of this Numba? Right. So that is obvious question. But thing is that here, if you see, Numba is adding some overheads, right? Because it has to convert that function call, right, into another optimized one, right? And it takes some time, right? It will introduce some overheads to convert that function, right? And that's the reason it is taking bit much time here. Okay, and why this is happening? Why these overheads are very significant? Because the computations are very less here, right? So if, and the runtime for this program is also very less. So it is in few nanosecond it is happening, right? So overheads are looking dominant here compared to the execution time, right? But if you see if you write a big program, right, or maybe the data is quite big, right, and computations are a bit complex, then you will come to know that, okay, these overheads are negligible compared to the overall runtime. So don't get frustrated if you're not getting performance by Numba and other libraries giving better performance. This is just because the function taking less time, and due to which the conversion overheads are a bit significant here. Okay, now what we'll do, we will try to see there is an exercise. Okay, before we move on to the exercise, first of all, you try to execute these previous cells and try to understand. I'll give you a few minutes. And meanwhile, I'll try to answer the questions in the chat. Okay, so you try till this exercise, try to execute all the cells before that and see the performance. Okay, sir, what type of libraries do we need to install to start CUDA programming in Python? Yeah, if you see here, there is a section here, requirements to use Numba. First of all, these prerequisites are there, system requirements are there, right? Type of hardware and everything, it is mentioned here. You just go through it, okay? And if you don't have GPU in your system, by default, this Numba compiler will optimize the code for CPU side. Okay, because if you don't have GPU, obviously there is no point in writing the parallel code for the GPU. Okay, try to execute those cells and let me know if you stuck at any point. Once you are done, just let me know. We'll move on to the next topic. Yes, so it is, as I mentioned earlier, Yashwardhan, everything is made available, right, in advance. So all the installations and everything they have completed at the back end. So you don't need to install anything here. Okay. But in case, let's say you want try to install in your local system or maybe in Google Colab, you will need to perform some installations using pip. Yeah, here it is mentioned, right? So first of all, what are the operating system you are using? These are the supported, right? Then Python versions, they are mentioned that either 2.7 or greater than 3.4. NumPy versions they have mentioned here. And the hardware is like NVIDIA CUDA GPUs, and its major version is supposed to be 3 and later. And CUDA toolkit that you are talking about, it is 8.0 and later, right? Uh, for AMD, they and ARM, they have experimental patches, so not complete support is available, right? And you will see Numba installation guidelines on NVIDIA platform. You will see. Okay, I think there are many blogs are available, so you can see same requirements, supported requirements are there. So whatever platform you are using, Conda, then use these, right? So using a x84 platform, pip you can use, right? So you can experiment that, right? So there are documents are available. Even some tutorials you will get to know that how to install and everything. Okay. It is not that tough to install any package in Python. Only thing is that your system requirement must be satisfied. You are not able to run the programs. I think just check whether your network is stable or not. If you are using uh, institute Wi-Fi or internet, then try to switch it to the local or your mobile hotspot. Okay. And if it is still giving some error, just refresh it and try to launch one more time. Okay. So should not be any problem. Okay. So now let's see this exercise. In previous case, the amount of time required to complete this hypod function execution was very less. So that's why the errors were significant. But now let's say here we have input size equal to approximately, I think, 1 million, right? And now what they're asking, we have to modify this code so that it will get optimized for the CPU side, right? So what is the first step? We have to import JIT from Numba. From Numba, import JIT. Okay. And here simply we have to use @JIT decorator here. And that's it. These are the changes you have to make. Now I'll execute these two cells, and here there is a assertion is mentioned if your implementation is wrong. So this will give you error, or else it will not give any message. Okay, so there is no message from this assertion. So that means your implementation is correct. And now we will see the performance difference here. Okay, so here you can see I executed Monte Carlo Pi. Can you tell me whether it is optimized or unoptimized? This Monte Carlo Pi? Yes, the first one is optimized one because we are calling the default function call. But if you are calling with the pi func, then you are calling unoptimized one. And you can see here, it is taking 371 milliseconds for the normal Python function to execute, and it is taking 10.8 milliseconds for the optimized by Numba version. Now, can you tell me what is the performance improvement in terms of speed up here? What will be the speed up here? Speed up means time required for sequential one or unoptimized one and divided by time required for optimized one. Yes, correct. So it is approximately 36 times. So simply divide 371 by 10 and this will give you approximately 37 times performance. Right? So now you can appreciate here because here the runtime is in milliseconds, right? So here also there are a function conversion overheads are there, but those are negligible now because overall runtime is in millisecond, 371 millisecond, approximately 0.3 second. But earlier case, the performance was the time was in nanoseconds, so that's why it is not that negligible. The overheads were not negligible. Okay, so this is how we can optimize the normal Python function using JIT decorator. Okay, now these are the details of how Numba works internally. So if you are interested, you can go in the much more details of this compiler, how this bytecode analysis and everything happens. As of now, it is not required, but just if you are curious how this function calls happen and at machine level, what are the code conversions are happening, you can investigate that, right? It is completely optional. Now, there is object and no Python modes are there. Okay, it seems that many of you are getting error. Let me see first. Mhm. There should not be any error unless you are trying to make any other changes. Okay, do one thing for whichever cell you are getting error, copy paste that cell rather than pasting here the message. So whatever your code that you have written, just copy paste it here. Let me see whether your code is correct or not first. Okay. So now next section is object and no Python modes. So here simply just to get the message whether Numba compile is supported or not, right? So Numba as of now doesn't support the dictionary, right? So here you can see there is a function which is performing returning value from the dictionary and is accepting the dictionary data type, right? So that support is not available for Numba compiler as of now. So if you try to execute that, it is going to give you output. But you may be surprised that I'm saying that that is not supported. So how it is giving the output as value? Because if it is realized that that particular data type is not supported, that Numba compiler gives up and the default function gets executed. Right. So whatever output you are getting here, that is not optimized by the Numba compiler, but rather it is the default execution of this function. Right. So in this case, Numba compiler is not going to throw any error by default. Right. So I'm making a statement that Numba doesn't support dictionary-based computations, but still it is not throwing any error. So by default, it is not going to throw error. It just simply gives up and the default function gets executed. But let's say you want to ensure that, okay, give me message that or throw error if Numba is not supporting that sort of computation, then in bracket you have to use no Python equal to true. And if you execute this, you can see you are getting error now. And you are supposed to get this error in this cell. So don't get worried about I'm getting some error here. You are supposed to get error in this cell because you are mentioning no Python equal to true. When you mention no Python equal to true, that means if there is no support available for any specific data type in this function, then JIT is not going to switch to the default mode, but it is going to throw error that it is not supported. Okay, so it's your choice. Let's say you want to use simply JIT, and if it is not getting optimized by Numba, execute the default one, then simply use JIT. But let's say you want to investigate whether that particular function is getting optimized by Numba or not, then make sure here no Python equal to true, right? And now you can see it is throwing error. Typing error, that means it doesn't support this type. Okay, and in short, if you want to write, then you simply import njit. Okay, so it is just alias for jit in bracket no Python equal to true. So you mention here decorator njit and it will throw error. Okay, again, I'm repeating, you are supposed to get error in these two cells. Okay, so don't worry for that. Fine. So go back and execute these few cells from this exercise till this no Python. Okay. Once you are done, just let me know. Then we'll move for the next topic. Okay. So let's move on to the topic where we can use this Numba for the GPU. Okay. Now, before that, it is important to understand some universal functions in NumPy and that are referred as ufuncs. Okay. So I'll just give you a short introduction to that, but if you want to investigate it further, so you can click on that NumPy universal functions here. And if you are not much familiar with NumPy also, there is a quick start is here, right? But to understand this CUDA topic, you don't need to be expert in this NumPy library and these universal functions, right? So whatever required, we'll try to understand quickly here. Okay. So first of all, this NumPy is a library which help you to write well optimized code for the array-based computations, right? So you typically store the information in arrays and you have to manipulate those arrays, right? So sometimes arrays are 1D, 2D or 3D or many dimensions are there, and you have to perform some operations like find the smallest element in the array or perform the array multiplications or matrix multiplications, find inverse of the matrix. So that sort of operations you try to perform on the given data. And NumPy is the library which is having uh, all these common operations written in well optimized way. Okay, so you need to use this library if you have array-based computations. Now we will try to see important aspect of this NumPy library is universal functions, and I'll try to demonstrate this with the simple example here. So what we'll do, we will create an array A, and this is how we create the NumPy array by np.array function we call, and we pass this list with elements 1, 2, 3, 4. The same way, we'll create B array and we'll pass the elements here 10, 20, 30, 40. And there is an add function is available in NumPy which expect two input NumPy arrays and it will perform the addition. Okay. So if I execute this, you can see here, we are getting this additions element by element, right? So 1 is getting added to 10, 2 is 20, 3 added to 30, 4 is added to 40. So this element wise addition is happening here. Okay, so that is obvious because we have arrays of same size, right? And they are one dimensional. But there is another example here, np.add function I'm calling, but here I'm adding a 200. So this is a vector or this is array and this is a scalar value, right? So ideally we say that this addition is not possible because array and the scalar we cannot add, right? But here in NumPy, it is having a broadcasting operation is there. So let's say A is having elements 1, 2, 3, 4, and we are trying to add 100 to that. Okay, so this is scalar and this is a vector. So we cannot normally perform the addition, but in NumPy, the broadcasting operation is there, which will broadcast this 100 to all the elements of array A. Okay, so it will get broadcasted here like this. And now the addition will be performed, right? Again, you can see the addition is happening element wise, right? So 100 is getting added to 1, this, like this, right? So this is called as broadcasting operation, right? And the addition is called as element by element. Now, if you see, there is another example here. If I execute this, you'll see the addition will be 100 is added to 1, 2, 3, 4. So output is 101, 102, 103, and 104. Okay, this is if scalar is getting added to vector. But now let's say we have a 2 by 2 matrix, right? So we have an array, 2D array C, which is having 16 elements, and its shape, we are going to reshape it to 4 cross 4. And if you see here, this is how C array looks like, right? So it is a matrix. But now in this C array, I am going to add the array B, right? What is the array B? Array B is having elements 10, 20, 30, 40. Okay, so array B is having 10, 20, 30, and 40. Okay, and now you see this input C array is of size 4 cross 4, right? And here B array is of size 1 cross 4, right? So how to perform this addition? Because in normal sense, we cannot even perform this addition if you follow the linear algebra, because the dimension of this array is 4 cross 4 and the dimension here is 1 cross 4, right? So dimensions are different, so we cannot perform the addition. But again, in case of NumPy, uh, here it is the entire array is getting broadcasted, right? So this array is getting broadcasted to all the rows here. Okay, and now this array will be added to every row of this particular C matrix, right? So this first element become 10 plus 0, 10, 20 plus 1, 21, 30 plus 2, 32, and 40 plus 3, 43, and so on. So second time, it will be added to the second row, 10 will be added to 4, becomes 14, 20 is added to 5, becomes 25, and so on, right? And if you see, the addition is happening element wise now. 10 is added to 0, element 20 is added to 1, and so on. So these type of computations are called as universal functions in case of NumPy, right? And they are suitable to optimize both on CPU and GPU side. Okay, so now let's try to understand how this NumPy, Numba is going to help us to optimize these universal functions. Okay, now earlier we have used JIT and NJIT decorator to optimize the code on CPU side, but now we will use two different types of uh, decorators. One is vectorized decorator and other is vectorized with function signature. Okay, so vectorized decorator is used to optimize code both for CPU and GPU, right? So this will help us to optimize code both for CPU and for GPU. Okay, and this vectorize is applicable only if you have universal functions. If you have ufuncs, then only you will be able to use this vectorized decorator, right? So that means if you have in your function the universal functions, right, or the computations like element by element, then only you can use this vectorized decorator. Okay, unlike previously the JIT decorator that we simply used to for normal function execution. But if you have this universal function, then it is recommended to use this vectorize. Okay, and as I mentioned here, vectorize also help you to optimize code for CPU side and GPU side. And let's try to understand how it does. Okay, so now here I'm importing the different decorator vectorize, and here there is a function add 10, which is taking input argument as array, right? Because if you see here, nums is a numpy array we are going to create here, and add 10 is a function which is taking this argument, and what it is returning num plus 10, right? Now how this computation happens internally, we have numpy array that is passed to this particular function, and it is adding 10 to every element by using broadcast. So it is universal functions, and it is element by element addition is being performed. So it is suitable for vectorized decorator. Okay, so now if you see here, if you execute this, right, you are getting correct output here, right? So we have elements 0, 1, 2, 3 till 9, and in that we are adding 10. So 10, 11, 12, 13, 14, and so on. Okay, now this is for CPU side. But let's say you want to use the same, you want to execute the same function optimized on GPU side, then you have to use same decorator vectorize, but few more additions to be there, right? So vectorize, let's say now this add ufunc is there, and which is performing the addition of two arrays x comma x and y, or here the actual arrays we are passing is a comma b. In that case, you have to write in this list the function signature. And what do you mean by function signature? You just need to mention that what is its return type and what are the input data types here, right? So this add ufunc is taking input as integer 16 and integer 64, right? So because these are the two arrays, by default they are of type integer. Okay, and this function is going to perform addition of x plus y. So integer plus integer is going to be integer again, and that is the value returned by this particular function. So that is integer 64. Okay, and comma, you have to mention target equal to CUDA. That means this specific signature you have to use if you want to optimize or execute that particular function on GPU, right? If you remove this, then it becomes the optimization for CPU side. But if you specify this function signature and the target equal to CUDA, that means you want to execute it on GPU side. And if I execute this and see the output here, so you can see you are getting the correct output. So A and B are getting added, right? So what is array A? 1, 2, 3, 4. Array B is 10, 20, 30, 40. And you can see you're getting output desired. Okay. Now, question is, you can see here, you never declared memory explicitly using CUDA malloc managed. You did not mention any configuration of a number of threads and block. You did not use that global ID inside the function and everything. So you can see here, just by writing this signature on top of your function, all the things are happening internally, right? So compile CUDA kernel to execute ufunc, the allocate GPU memory for input and output, copy data from CPU to GPU, execute CUDA kernel, right, with appropriate kernel dimensions, right? Then copy the result back from GPU to CPU and return results to the NumPy array. So all the things are happening automatically, right? So though you are saying that by simply writing this line of code, the function is getting on executed on GPU, but internally it is performing all these operations, right? It is just reducing the overheads of the programmer, right? So it is making the programmer's life easy. Fine, but it supports only the ufuncs, right? If your function is not having ufunc, then you have to write explicit CUDA kernels, right? But if you have that sort of functions, ufuncs, then definitely it is recommended to use this vectorize because it will save your time and number of lines of codes also. Okay, now coming to the point, let's see how this NumPy addition on CPU and GPU are giving different times. Okay, so ideally what we want, the GPU function is supposed to give you better results, right? So they are supposed to execute faster. So CPU version is taking 1.18 microseconds, but GPU is taking 702 microseconds. Now, can you tell me what's the speed up here? What is the speed up? Yes. No. Right. So here speed up is not 700 or 600 times because this is CPU version and this is GPU version. So we have to divide CPU by GPU version. CPU version is 1.1 microsecond and GPU is taking 700 microsecond, right? So it is less than zero. And practically, if you see, this is what we are not wanting to see, right? Because GPU version is slower than CPU version. Okay, that is completely opposite to what we are expecting. Okay, now here GPU version is slower than CPU. And the reason is, first of all, input size is very small, only 4 elements we are adding. It is just like we are asking 100 students to shift one chair from one classroom to other classroom. So obviously there is no use of that 100 student to do that. Okay. Second thing is calculation are too simple. We are simply performing one addition, right? So for that GPU is not required. And to do that sort of small computations, we are copying data from CPU to GPU and GPU to CPU. So obviously those are the overheads associated with that. And here our data types are larger than necessary. Okay, so if we don't need 64-bit addition required, so we can do it in 16-bit also or 32-bit also. Okay, so these are the things that we have not taken care, right? And that's the reason our time is very much than CPU one. Now what we'll do, we will take this example and we'll see whether its performance is improving or not if the input size is more. Okay, so again, there is a Gaussian PDF function is given to us. So you don't need to investigate its mathematical significance, right? So forget about that. We'll simply observe the computations. Okay, so this is the NumPy array of size 1 million. It is created, right, using the random uniform function. Then the mean value and sigma values are initialized here. Then Gaussian PDF function is getting called and it is going to take input argument as x, then mean and sigma. Now we want to execute this function on GPU because it is performing the vectorized operations here. So what we can do, first of all, we will use @vectorized decorator, and here I am passing the function signature, right? So this function is taking 3 arguments of type float. So 3 arguments float are there. It is returning the float value. So return value is also float, and then target equal to CUDA. Okay, so now if I execute this, so this is a to compare there is a library in Python, SciPy stats, and from that we are calling this normalization function, which is taking 66 millisecond, and the Gaussian PDF that we try to parallelize here, it is taking 4.36 milliseconds. Okay, so you can see clearly we are getting approximately 15 times performance here because your data is increased, right? Computations are complex and the data transfer between CPU GPU is negligible if the computations are heavy and input size is more, right? So 1 million computations are there, and uh, computations are complex because we are calculating exponential, then multiplication, then square, then division, then again division, multiplication. So computations are a bit complex here, right? And that's the reason you can see now the SciPy library based sequential implementation is taking 66 millisecond, and our own version of GPU is taking only 4.36 milliseconds. Okay, now what we'll do, of course, on GPU we got the performance. Now let's try to see how much performance we'll get on the CPU side. So if you want to optimize this Gaussian PDF on CPU, only use the @vectorize. No need to pass the signature here and the target equal to CUDA. By default, it will optimize for the CPU side. So let's take CPU side, how much it takes time. So it is taking 23 milliseconds. Still, it is faster than the SciPy library-based implementation, 3 times. Okay, so you can see here GPU version is 15 times faster compared to the SciPy library, and CPU based implementation is optimization based is 23 times, sorry, 3 times faster. Okay, so this is how we can get the better performance in case of this Numba compiler. Okay, so take your time now and 5 minutes to go back and start executing the cells from these universal functions. Okay, I'll give you 5 minutes, execute all the cells, see the output, observe the performance, and if you have any queries, just let me know. Yashwardhan, that's what I'm trying to say. You don't worry about those details, right? So this is the SciPy library based implementation is there for the PDF function. You're not calling this your own function here, Gaussian PDF. You are calling this SciPy based library function and forget about its parameters, right? Log scale, I think means that what is the mean value and the standard deviation value. Okay. But you don't have to go into the details of that. You just simply observe the performance. Okay, the question related to your scikit-learn library. In that case, uh, you have CUML library. That is the uh, parallel implementation of scikit-learn based algorithms, right? So CUML, you can search, and I think CUML now you can use it in your Google Colab. So we just explore how to use CUML that will accelerate performance of your machine learning models from scikit-learn library. Right? So its parallel version is already available in this library. Let me know once you are done with this executions. Okay, so let's complete this topic, CUDA device function, and then we will have a break. So, so far we have seen we are trying to optimize this uh, Python function, and we want to execute on GPU using this vectorized decorator with type signature and target equal to CUDA. Now, if you see here, this polar distance function is given to us, which is expecting some arguments as rho 1 theta 1, rho 2 theta 2. And this function internally calling another function, polar to Cartesian function. Now, we said to compiler that this function is supposed to execute it on GPU, right? But this function is, if you don't use as of now, consider this is not placed here. Now, in this implementation, what happens? This polar to Cartesian function is on CPU side. Okay. Now, what is wrong here? We have, let's say, this CPU and this is GPU. So this polar to distant function is getting executed on GPU, right? Polar distant function, but it is calling another function here that is polar to Cartesian. But this polar to Cartesian is defined on CPU side, right? Polar to Cartesian. Now, what is wrong here? We have this data, rho 1, theta 1, everything now shifted to GPU. But now inside that, the computations are happening on CPU side, right? So it is calling CPU function. And when you are executing any function and then you are referring to the CPU function, it is not allowed, right? And which is obvious, right? Because you started executing on GPU and thread is calling a function on CPU side. So that is not possible because you cannot directly call a GPU CPU function from inside the GPU function, right? So that function is supposed to be executed on CPU, GPU only. So polar to Cartesian function is supposed to execute on GPU. Now, by default, if you don't mention anything, it will get executed on CPU, supposed to get executed on CPU, and that is wrong. It will throw error. Now, how to tell compiler that this function is called by the GPU function, right? So in that case, you have to mention here JIT, right? CUDA.JIT device equal to true. So when you mention this device equal to true, that is indicating that this function is getting called by some other function that is currently executing on GPU. Okay, so this is the way you can tell to the compiler, and then your implementation will be correct here. Okay, so now if you execute this, yes, Harsha, you are asking why not JIT only, right? If you mention it JIT, then what is, you tell me what is its significance? If I simply mention here JIT, it is trying to optimize on GPU, the CPU side, right? If you recall here, the JIT decorator we have used to only optimize function on CPU side, right? But now what is happening here? You are calling this function, right? Polar to distance, polar to Cartesian function is getting called by polar to distance function, right? And that is already executing on GPU. Okay, so let me again rephrase it. You have a function that is getting executed on GPU, right? So the function name is polar distance function. Now, if it is getting executed on GPU, right, it is going to create number of threads, right, to execute. Now, these threads are supposed to get executed on GPU side, right? Because you created number of threads to execute on GPU side. Now, what is happening inside this? It is every thread is calling polar to Cartesian function, right? So if it is calling polar to Cartesian function now, so every thread is supposed to execute that function on GPU only, right? So we must have some kind of uh, uh, message to the compiler that, okay, this is supposed to be executed on GPU side only, right? So if you don't mention this, what happens? It will assume that this function is supposed to execute on CPU. And now how it is possible that a CUDA thread that you created in this function will execute on CPU side? Right, so it is not possible, right? A CUDA thread is executing on CPU side. That is not possible. So we need one mechanism to tell compiler that, okay, these functions that are getting called inside this GPU function will be executed on GPU only. And to tell that, we are mentioning @CUDA.JIT, and we are mentioning device equal to true. Device equal to true means those are supposed to be executed on GPU, right? GPU is sometimes referred as device and CPU is referred as host. Okay, so that's the way we need to ensure that the function to be executed called inside the GPU function to be explicitly mentioned as with the decorator @CUDA.JIT device equal to true. That's it, right? So in this section, only this thing you have to remember. Okay, so you execute this and you will get the results. Fine. So far we have understood how automatically we can uh, optimize codes on both GPU side and both on CPU side. Okay. Now there is an exercise here for GPU acceleration function. Okay. So you try to attempt that. Okay. We will have a 10 minutes break here. In meantime, if you get time, you try to solve it and see the output. And if you're not getting, there is a solution is supposed to be there somewhere. Yeah, you can see the solution is there here. You can click on that and you can check, right? So we will take short break here for 10 minutes and we will resume the session at 11:10. Okay. Okay, so let's continue. They have given us GPU exercise as GPU acceleration function. And what we have to do is we need to convert this zero suppress function so that it will be executed on GPU. Okay. So if I execute this without, executing on GPU, right? So it will throw error here. And this function is simply performing zero suppression, right? So what are the values that are near zero? Those will be treated as zero. Okay, that is called as zero suppression. Now you don't have to make any changes here, right? So you will keep it as it is, and this function we need to optimize. Now this function is simply performing what waveform value it is comparing with threshold. If it is less than, it is result will be 0, and else result will be waveform value. Okay, and it is returning result value. So see the type of data. So for waveform it is integer 16, right? Then for threshold it is also integer, right? So we need to use vectorized decorator, right? And in bracket here we have to pass the function signature as list, right? So we will mention here int 64, that is return type. It is expecting two values, int 16 and int 16. Okay, and then we will mention target equal to CUDA. Let me see the syntax properly. It is outside. Okay, it is like this. Target equal to CUDA, right? So yes. Okay, so if you make those changes, now you can see here, it is going to give you 0 suppressed output. Right. So this is the only change you have to make by adding the vectorized decorator. Fine. So this is about how to use vectorized decorator. And so far we tried to uh, perform optimizations on CPU side and GPU side. Okay. We were not aware about how data is being transferred from CPU to GPU or GPU to CPU. Now, if you see, the data transfer is nothing but the overhead, right? Because if you are writing normal CPU function, then there is no data transfer. If it is getting executed on CPU, there is no data transfer. But if you want to execute any function on GPU, the data transfer happens from CPU to GPU and GPU to CPU also. Okay, so let's say this is CPU and this is GPU. Now what happens when you execute any function on GPU, the data is initially residing in CPU memory that will be transferred to GPU first, right? For example, in this add ufunc x and y, you are passing it to the GPU function. So initially x and y will be available on CPU memory. That you need to transfer it first, and whatever the function is returning, that will be transferred back to CPU. Though it is not visible for us, but internally it is performing this data transfer. And obviously, this data transfer is nothing but the overhead, because before you start computation or optimization on GPU side, the data transfer need to be taken care. And whatever result you are getting, you need to again transfer the result back to CPU side. So this data transfer is called as overhead, right? And we need to optimize these overheads also. We need to take optimal decisions on where at what point we have to transfer the data and at what point we have to get the data back from the GPU side. Okay. And the default behavior of any GPU function you execute using vectorized decorator, first it will transfer all the required input data values to the GPU. And whether you want it or not, it will transfer the whatever return values there on the CPU side. Okay, this happens to every function that you execute on GPU. Let's say you have two functions, f, right? This is the function f1, and there is another function f2. Now f1 is getting executed on GPU. Now what happens? The required data will transfer from CPU to GPU, and output will be transferred back to GPU to CPU. Again, f2 is executing on GPU, so required data will transfer on GPU, and output will be transferred back to the CPU side. But what if the output of f1 is required to f2, right? So in that case, what is happening? We don't want f1 to send the data back to CPU side, rather than keep it on GPU side itself, so that that can be taken as input to the f2, right? But in default behavior, what is happening? F1 is returning value x, let's say here on the CPU side, and that x is taken as input to the f2. Again, data transfer from CPU to GPU will happen for f2. Right. So these are the conditions not taken care if you rely on the default behavior of this vectorizer. Okay. Now what we'll do, we'll try to understand how we can do this manual transfer and everything to optimize this data transfer. Okay. So let's execute this function, and we'll see as of now how much time it is taking. So this is the add ufunc function we are calling. It is taking two input arguments, x and y. Okay. And it is returning addition of x and y, right? So what is x and y? So if you go back and see somewhere, x and y might be mentioned. Okay. So x is defined here. Where is it defined? Here itself? Okay, sorry. X and Y are defined here itself. So input size is 100,000, and X is of same array, and Y is of also array size same. So the X and Y arrays of size 1 lakh, and these are the initial values of those X and Y arrays. And this add ufunc is performing addition of these two arrays. Right now, you don't know what is happening internally, but let's see logically what is happening. Okay, so again, I'm giving you logical picture here, CPU and we have GPU, right? We know that CPU and GPU have their own memories. Now, if you see X and Y, these are the two arrays defined by NumPy library, right? So when it is NumPy library, that means it will allocate memory on the CPU side. So X and Y are now on CPU side with this initialization. But you are calling this function add ufunc on GPU by using this decorator, right? So add function here is there that is taking two arguments X and Y, and it is getting executed on GPU side. So it will transfer internally the values of X and Y to the GPU, right? And what this add ufunc is returning, it is returning X plus Y, right? So this X plus Y will be returned back from GPU to CPU. So X plus Y is transferred back to the GPU side. So this is the result. Okay. Now, what if we initialize or transfer the data in advance, right? Because whatever time we are measuring here, it is taking 1.14 millisecond, and which covers the data transfer time also. We are transferring X to Y first to GPU side and the result back to CPU side. So this overall time is 1.14 millisecond, which consists of this data transfer time also. Because to perform this computation, we need to perform the data transfer. Okay, so what we'll do now, rather than having this implicit data transfer, we will do one thing. We will try to copy the data in advance to this GPU, and then we will measure the performance of this add function. Okay, so what if we transfer the data in advance to the GPU side? Then we'll see how much time this add ufunc takes. Okay, and to do that, we have functions in this CUDA here to device function. Okay, so here we are calling CUDA.toDevice function and we are passing X as an argument. So X is a NumPy array. We want to transfer it to the GPU. And that GPU array will be referred by this variable X underscore device. So this is the normal nomenclature that we follow. X underscore device means that array is stored on the device. You can give any name just to distinguish between CPU arrays and GPU arrays. We are going to mention it as X underscore device, right? So this is X underscore device equal to whatever data we are transferring X from CPU to GPU, right? So here what is happening now? We are transferring the value of X to GPU, right? So this will transfer the value of X to GPU. X will be there and that will be referred as X underscore device. Okay, so entire array is transferred. Same way, we'll transfer Y to the GPU and we will refer it as Y device, right? Note that we have two copies of data, X and Y present on CPU side and X device, Y device present on GPU side. Okay, now if you execute this cell and we'll see the type of data here, X device is CUDA array now. Earlier X is, if you try to see, it is NumPy array, but X underscore device is CUDA device array now. Okay, its shape 100,000, that is the same as of X here, and its data type is float, that is okay. Now if I see the how much amount of time it takes to perform this add ufunc, but note that here I'm not passing X comma Y, but I'm passing here X device and Y device. Those are already present now on the GPU side. Earlier, this add ufunc, when you used to call, the data transfer used to happen first, then the addition, and then the data will be transferred back to the CPU side. So though that time was also considered in this add ufunc. But now we have already placed these arrays on the GPU side, and while calling this function, I'm passing X device and Y device, and you can see here how much time it is taking. It is simply taking 570 microseconds. right? So you can see how much time it was investing on the data transfer. Earlier it was taking 1.14 millisecond, but now it is taking only 570 microseconds. Okay. Also note that here it is also transferring the data back here. Okay, so though we already transferred X and Y in advance to the device, but here in this case, it is transferring data back. X plus Y result, still it is transferring back. Okay, now what we can do, what if we will not transfer the data back to CPU, we'll keep it on GPU side. We don't want to transfer the data because it is a default behavior of this vectorized function. It will automatically, if you don't mention anything, it will automatically transfer the result back to the CPU side. Now what I'll do, rather than transferring this data back, I'll create a new variable here, right? I'll create a new variable, and in that variable, I'll allocate new memory on the GPU side, and where I will store the result X plus Y, and I will not transfer this back to the CPU side, right? Now, when you try to time it, then it will purely measure the amount of time required to complete that add function. Okay, and how to do that? So obviously, if I want to store the result of this on GPU side, first of all, I need to create a new variable, right? And I need to allocate memory to that variable. So how I can do? There is a way we can do that using CUDA.deviceArray function we can call. We can mention how many elements you want to allocate and what is the type of data in that array. Okay, so this is going to give you a new out device array, right? So that is going to store the X plus Y. So this is going to be out device array, for which we are going to allocate memory, and it is going to store the X plus Y addition in that array. And now what is happening? This function neither copying data while getting executing from CPU to GPU, nor it is copying the result back to the CPU side. So it's simply performing the vector addition of two arrays on the CPU side only. And data transfer we have taken care explicitly. Here we have transferred the data using CUDA to device function from CPU to GPU. And here we have created new array to hold the data that is being generated by this add function. And how we can tell that the results to be stored into this GPU array? We need to simply mention here add ufunc pass X device, Y device, and here out is a new variable we have to mention and equal to out device that we have created in this variable. Right. So what is this function is doing now? This function is taking X device and Y device as input. They are present on the GPU side, and output of the whatever this add ufunc is going to return, that you have to store into this out device that is also on the GPU side, right? So explicitly you are telling by making out equal to out device means whatever output of this function is there, you store into this out device variable. Okay, and let's try to see now how much time it takes to execute this function. So first execute this out device and then execute this function, and you will see here the time required is 550 microseconds. Right? So earlier it was taking 570 because data transfer for X plus Y was there. But now we also removed that data transfer, and now it is taking only 557 microseconds. Okay. Now, so if let's say that out device you want to copy back to the host side or the CPU side, right? Because output you stored over there. Now let's say at some point you need that data, then explicitly you call this copy to host function, right? And out host is a variable that is holding that value, and out device is a variable that is pointing the data on the GPU side. We are calling on that copy to host function, and that will copy the result back to the CPU side. So out host is on now CPU side. Fine. Okay, so what I'll do, I'll quickly recap what is happened here in this particular function. So this is the add ufunc, right? That is vectorized using this target equal to CUDA. So for this particular function, data transfer was happening. So X and Y, this is GPU, this is CPU. So before you call this function, X and Y explicitly, so implicitly transferred on the GPU side, then it will perform X plus Y and it is return this value. So addition used to transfer back explicitly, right? So now it used to take 1.14 millisecond. And what we did try to perform, so we don't want to transfer that data while that function call is happening. We will transfer it explicitly well in advance. So these two are the functions we are using, two device functions. So before function call, they'll transfer this X and Y value on the GPU, and we don't want this X plus Y to transfer by default on CPU side. We will create new out device array to hold that X plus Y. Okay, and to do that, first of all, we have created a new array using CUDA.device array function of size n, and data type is equal to float 32. And then if you see, the function is defined as like this, so called as like this, add func is there. Here I'm passing X device and Y device. Those are already present on the GPU side, right? And output will be stored into the out device variable that is already created on the GPU side, right? And to get the data back from GPU to CPU for out device, we will use copy to host function, right? So this is what the memory related operations we perform explicitly, because we don't want to rely always on the compiler to transfer the data, because by default, if we are calling 10 functions, so it will copy paste the data 10 times to and fro to the GPU. Sometimes we don't have to copy data back to the CPU side. We need to keep the data on the GPU side itself. So in that case, we have to take care of these scenarios. Okay, so take your time. I'll give you 5 minutes to go and execute these cells from managing GPU memory till this exercise. Okay, so execute that and try to understand what these functions are doing. Okay, so there is an error in previous case. It will give you error because here int 16 is the data type that is mentioned for where and in signature, if you are trying to give it 64, type mismatch will be there and there will be error. Okay, so any other query you have, you just mention in the chat box. We'll try to resolve it. Right? Understand this is very important, because once you understand this thing, you will be able to pass this chapter 1. Okay, because in chapter 1, only your assessment will be based on how you optimize the data transfer. Right? Try to understand when you are transferring the data from CPU to GPU, when you need to transfer data back from GPU to CPU, and what are the functions that are used to create array and to transfer the data. Okay, done. Okay. So now there is an exercise to optimize memory movement, and pay attention carefully here, because similar there will be exercise available for here assessment, and for which the solution is not available. Okay, so try to understand how I'm trying to understand this data transfer first, and then how we are going to optimize it. Okay, so if you see here, they have already made this make pulses function is there. They already tried to execute in parallel. Okay, and it is expecting arguments as noise is an array of size 100,000. Then t is also of the same size, and period is scalar value. Okay, and these are the values it is expecting. So n, sorry, it is expecting I, right? So it is transferring t value that is of size array of size 100,000. Then period is scalar value and the amplitude is a scalar value. So these are the values it is expecting, and is returning max of some value. So it is also float type. Okay. So this is the function. We will execute it. And now what they want us to uh, execute this particular function by optimizing the data transfer. Okay, now what we'll see, we'll try to understand first what is happening here. So this make pulses function is calling, let me make a block diagram here of CPU and GPU. So this is your CPU, this is GPU. Okay, so make pulses is a function that is getting executed on GPU side, right? So make pulses is getting executed on GPU side. And to execute that, what we are passing t, period, and 100. Okay, what is t? T is an array. So t array will be transferred. Okay, from CPU to GPU in order to perform this computation. Then whatever output is there of this make pulses will be transferred back or returned to the CPU side. So we have here output of this make pulses function will be transferred, and it will be placed in the pulses array. Okay, so this is what happening in this first line. T array is getting transferred along with the small values of scalar, period, and amplitude. Those will be also transferred. So, but those are only single values, so it won't affect much. But T array is transferred from CPU to GPU. And then output of this make pulses is getting transferred from GPU to CPU, and it will be placed in the pulses variable. Okay. Now, second function we are calling add ufunc, and that add ufunc we already parallelized in the previous case, right? Add ufunc, and that is getting executed on GPU. So this add ufunc is now calling on GPU. So we have this add function also on GPU, and which is expecting what argument? Pulses and noise, right? So noise is also on CPU side, and pulses now that is output of make pulses is also on CPU side. So noise and pulses on CPU side both will be transferred from CPU to GPU. So this will be transferred as input to add, and this is to add. And these two are returning, this add ufunc is returning the value back to CPU side again, and that will be placed in the waveform. Okay, so that you need to first of all make logical picture of this function call. If this logical picture is clear, then definitely we will be able to solve it very easily. Right. So I repeat the statement here because this is very important to understand. That's why I'm repeating many times. So we are having this make pulses function call. Make pulses function call is there, and that is expecting arguments t. T is an array, right? So to execute this make pulses, the t array will get transferred to the GPU side. right? Then this make pulses will complete its execution and it is going to return these values, and those values will be stored into the pulses, right? Where the pulses is there on CPU side, right? By default, it will be on CPU side. So make pulses output is stored in the pulses here on CPU side. Then add ufunc is the function which is taking two arguments, pulses and noise. Pulses and already noise is there on the CPU side because it is defined using the NumPy array. These two will be transferred to the GPU, right? And add ufunc will perform some operation on that, right? And the output of this add ufunc will be transferred back to the GPU side. Okay. Now, once you get this data transfer diagram, now question is how we can optimize the data transfer. Now you can see, can you tell me what is the redundant data transfer here happening? For which array unnecessary data transfer is happening? For which array unnecessary data transfer is happening? Noise, it is required, but for pulses, I would say, okay, because first of all, this pulses is getting transferred to CPU, and then again CPU to GPU getting transferred because add ufunc is required, right? So what we'll do, we will try to optimize this pulses data transfer. Okay, and how we can optimize? We will ensure that output of this make pulses will be stored on the GPU itself, and the same will be passed to the input to this function. Okay, now to do that, what we have to do? For that, first of all, we need to create an array on device. Okay, because we want to store the pulses on device. So we will create dpulses array, and to create an array, we have function this CUDA device array. Okay, so I'll use this dpulses and its size is going to be n. Okay, so now what happened? We don't need to transfer the data to dpulses because we have created this array. So we'll remove this statement pulses equal to, and here I will mention out equal to dpulses. Correct? Because now what is happening? This make pulses function is performing whatever operation is there, and it is storing the output of that return value of that make pulses in the dpulses. Where the dpulses is there, now we created the dpulses on the GPU side. Okay, so we don't need this pulses here. We will keep the pulses or d underscore pulses here. Okay, so this pulses to GPU data transfer is not required. Okay, now what change you have to make in the waveform or add ufunc function here now? Yes, that is dpulses because we are already data is available over there. Okay, so I'll execute this and you can see you are getting the similar output again. Okay, so this is what I try to make changes to avoid the data transfer. Okay, so if you see the solution, I hope it is the same solution that we have created. Okay, dpulses they have created. They have transferred this DT and everything to the device in advance, but that is not redundant one because they anyhow they have to transfer the data. But the unnecessary transfer was related to dpulses that we have taken care. Okay, now based on this similar thing, there is an assignment, and I'm not sure who yesterday was asking about how neural networks are getting executed on GPU side, right? So there is a small assignment is there where we have to accelerate the neural network calculations. Okay, again, it is not necessary. You have to understand what is a neural network and how the computations are supposed to be performed, right? It is just a small assignment that is given to indicate how we can accelerate the performance of neural network computation. If you don't know, don't worry. We'll just observe it from the compute point of view. Okay. Now, here, this is the assessment from this chapter. What you have to do, you have to accelerate neural network computations. And here they have mentioned some imports and initialization. So grayscale is the initialization is there, weights is also initialization, and input size is 100,000. Okay, now what they are expecting us to accelerate these, first of all, three functions, accelerate using vectorize to be executed on GPU. Okay, then there is a hidden layer function is there, create hidden layer function, which is taking these arguments. And what you have to do, you have to observe these computations, how in which the order they are happening, and you have to optimize the data transfer. Okay, so first of all, you have to convert them into CUDA, sorry, vectorize and the CUDA functions, and then you have to optimize the data transfer here. Okay, so remember that this is the main function, create hidden layer, that in which you are calling these normalize, weigh, and activate functions, and these are the currently defined on CPU side, right? Do not change any of these arguments, right? Whatever data transfer you have to do it in here. Okay, and don't even touch this, right? Don't touch in the sense, don't try to modify anything in this particular cell, or else you will lose the assessment criteria, and then you will never be able to assess even though your submission is correct. Okay, so these two cells keep as it is, don't try to touch it. Fine. So first of all, what we will do, we will execute this as it is, and we'll see its output, what it is telling. Okay. So without any modifications, I will run the assessment. Okay. So now it is telling that it is trying to assess your submission, and it is going to give you feedback whether your submission is correct or not. And let's wait for a few minutes, because it is a sequential one. So first of all, it is telling that your function returns CPU array. It is true, but currently it is taking 6 seconds, and it is supposed to run less than 1 second. Okay, so it is false, and it is asking us to please refactor your code. That means your application is not running fast enough. So what we'll do, we will go back now and we'll try to do those modifications. Okay, now before that, they have also mentioned that don't use this exp, we have to use exp from math, right? So what I'll do, from math import exp, because if you use NumPy based exp, then it will be calling the exp function on CPU. So math exp, which allows to execute on GPU. Now let's try to understand what is happening in this create hidden layer. Okay, so again, on paper, try to draw that block diagram. So on CPU we have, there is a GPU. Okay, so now what is happening? We want to convert this normalize, weigh, and activate function as GPU function. Okay, so first of all, we'll try to do that. This normalize function is expecting argument vectorize, and yeah, I'll always forget that commas where you have to mention. Okay, we want to vectorize this. So this normalize function, its input type is grayscale. Sorry, input is grayscale. It is of type float 32. So we have to mention float 32, and it is expecting only one argument. So remove the remaining arguments. Okay, it is also returning the float, so that is fine. So this is how we make the parallelization of this normalize on GPU. Same way, we will do the weigh function, which is expecting two arguments rather than one. So both are of type float 32. Okay, and finally the activate, which is expecting again float values, and we are making it as a target equal to CUDA. So we try to optimize or parallelize these three functions using vectorized decorator. Okay, now with this minimal changes, we will try to execute all these things again, and we'll see whether it is running less than 1 second or not. Earlier it was taking 6 seconds, but now let's see how much time it is taking. Okay, it is taking 1.2 second, right? From 6 second, it is drastically dropped to 1.2 second, but our criteria is it is supposed to take less than 1 second, right? Now we parallelized, but our memory transfers are not optimal. Okay, so what we'll do, we will see now the pattern in which data is getting transferred, right? So we have normalize function. Now all these normalize way and activate functions are getting executed on GPU. So we have normalize function, then we have wave function, and then we have activated function. Okay, so these are getting executed on GPU. So this is GPU, this is CPU. Now see what is the input for normalize grayscales, right? So input for normalize grayscales, and this grayscale is currently on CPU. Okay, so it will transfer the grayscales here, right? This is the pattern. Okay, you cannot apply vectorized to hidden layer. The reason is in this we don't have these vectorized computations, right? Universal functions are not there. There are function calls inside this create hidden layer, so we cannot directly apply vectorize here. Got it? You cannot vectorize because this is not you can say universal functions. You may say that CUDA dot JIT equal to device equal to true, but here you don't have universal functions, right? These are the arrays you are passing here, right? These are getting called only once. We don't have to call these functions by multiple threads. Getting it? But inside this function, we are achieving parallelization. Okay, there is a difference. Uh, why this function you cannot parallelize? Because these are the functions we not calculate call only once, not multiple times. Okay, just a second. Okay, so here, as I said, this function is not having universal functions, right? Element by element computation, rather than function calls are there, and these are supposed to be called only once. So we cannot optimize or parallelize this one. Now, coming back to the data transfer here, we have this grayscales first transferred to the from CPU to GPU, and it is returning some value, and that value is normalized. Okay, so output of this will be transferred back to the normalized. Okay, this is the variable normalized. Okay, then wave function is taking two input arguments, right? Normalized, that will be transferred to wave function normalized, and there is another variable weights. Okay, these two will be transferred to the GPU for performing this weigh function. Then we have activate function, which is expecting, sorry, weigh is going to give you output as activated, sorry, weighted, right? I'll mention WTD for weighted. Okay, and these weighted will be taken as input to activated. Okay, and this is going to return value as activated, right? So these are the data transfers happening. Okay, so here what we'll do, we will avoid all the types of data transfer except the last one, because there is a criteria for the last one is you need to explicitly copy that. Okay, so for that reason we will copy that, but we'll try to optimize this data transfer. Now you tell me, how will you avoid this data transfer? So how will you avoid the data transfer of this grayscales to GPU? First one. How will you avoid the data transfer grayscales to GPU? Yes, so that means you will already create a degrayscale variable, allocate memory to that, and you will keep it on the GPU itself. So this is avoided. How will you avoid this norm? What is mm, normalized data transfer? Yes. So what we'll do, we will create denormalized array on the GPU side, and output of this will be stored and the denormalized here. Okay, so these two data transfers are avoided. Now this also avoided because uh, to calculate this wave function, denormalized will be available on the GPU, and weights is there that we will also create on the GPU, d weights. Okay, we'll keep it on GPU, so this transfer will be avoided. Then the wave function is returning weighted value that is required in the activate function. So we will do one thing. We will also create this weight de-weighted on the GPU side. Okay. And then we will use in the here. Okay. So this data transfer is avoided. So all these data transfers we can avoid except this, because explicitly they want us to transfer the data, copy back to the host. Okay. Because that is the final result we want. Fine. So this is what expected. So now what we'll do, we will try to apply this logic step by step. Okay. So we have grayscales and weights. So corresponding D grayscales and D weights we will create here. Yes, activated copy to host will be there. So what is that to device function, right? So X device equal to device. So we will use D underscore grayscales to device, and it will transfer grayscale values. Same way we will use weights, and we'll use weights here, D weights and weights. Okay, now D grayscales and D weights are already available on GPU side. Okay, now what changes we have to make here? We have to make D underscore grayscales and D underscore weights here. Now we want to store output of this into normalized array that is on GPU. So we will target now this normalized one. So what we will do, we will create a denormalized array. Okay, so denormalized array we will create, and sorry, we need to allocate memory, and to allocate memory we have function device array. Okay, and its size is going to be the same as n. Okay, so denormalized array we created, and here what changes you have to make? Out equal to denormalized. Okay, so what is happening now here? We don't need this normalized, and we make it here denormalized. Now what happened here? We created an output array for this normalized function, denormalized, and output will be stored here. So the normalized function's output will be stored in the GPU, and we will use this denormalized as input to the weight. Okay, now D for these also two inputs are there. Those are already present on the GPU side. Then we need to create a output array for storing the weighted value, right? So we will create D-weighted, and we will allocate memory using CUDA device array. Okay, and this weighted is not required now. We will create here out equal to D weighted. Fine. and whatever output is there, we will use here deviated, and activated, whatever output is there, we will use copy to host. Copy, what is the syntax? Copy to host, copy underscore to underscore host. Okay, so these are the changes we have made. I think it will throw error. I'm suspicious. Definitely, yes. Deviated is not defined, so we have to change d. Where is that? D underscore weighted. Yeah, this is the error. Okay, value error reshape changes the size of array. D weights. Normalized and all of this size. Do you find any error that we have made while doing this? So CUDA device array we created. This also we created, deviated. Their size is also same. Let me comment out this and check whether the error persists same.
Sir, you can assign that activated.copy to host to a variable and return that variable.
Yeah, I think deactivated, right? Activated will create a new array and out equal to deactivated and deactivated copy to host. Let's see. Activated is not defined. Activated, where is that?
Return deactivated, sir.
No.
Actually, we have to assign that name for that big.
Even after you refactor this code to run on GPU, make sure activated back to the host. Can we make here activated? I'm not sure whether they are taking the names correctly or not. Let's see, we'll change this to D grayscales, D weights, then normalize is the function, weight is the function, activate is a function. So let's see if this works. Grayscales. Okay, they are even not allowing us to change these values. Okay, we should not change these values. Let's define them inside them.
Sir,
Hmm?
sir, define assign the activated dot copy to host to the variable activated.
You mean to will keep deactivated as it is and activated. Is it right? You mean to say right?
Yes, sir.
After a long time, I'm opening this Jupyter notebook. Even I also forgot that. Okay, results are getting correct. Yeah, it is working fine. Okay, that was the error related to that copy to host syntax, right? So you can see now it is running fast and it is taking less than 1 second. That is true. Okay. So once you complete this, you get successful message. Again, you have to go back and click on assess task. Okay. In my case, it is already showing passed. You click on that assess task. So first chapter will be completed. Okay. So the first change you have to make is remove that import exp from NumPy and import it from math. The second thing is you have to apply the vectorizer for all these three functions. Okay, then make changes into this function. Okay, so I'll share this for your reference. First, try it by yourself, understand what changes you are making. Shift enter. Then second cell is this. And third cell is this. Okay, so these are the changes you have to make in order to complete. Right? So go back and click on assess task. You will be able to generate the get the message successful execution. Paul says no. Is there any question? Okay, then Yashwardhan, I'm not sure which what question you're asking. Why not array? Okay, so all of you are able to get successful message. Just quickly raise your hands. Those who are getting successful message. Quickly raise your hand if you are getting successful message. Only 5 students, 5, 6 students. What about others? Okay. Try to complete during session itself so that it will save your time later on. Okay, and that's the reason I'm trying to introduce with the assignment during the session itself so that in future you can explore other things. And it's bit tough to answer to the queries after the training is over on WhatsApp. So it is better to resolve your doubts and try to complete the assessment during the live session only. Okay, you try it for 10 minutes. Okay, those who are not getting, we will resume the session at 12:30. We will take a short session at 12:30 till 1, and from 1 to 2 we will have a break. Okay, so at 12:30 try to join, and those who have completed this grading, go and stop this task and launch the second chapter. Okay, so second chapter is quite easy because you have already aware about the custom CUDA kernels in C++, so we will quickly finish that. So here you launch the cloud instance of second, wait for 5 minutes. Okay, so I'll be back in 10 minutes. At 12:30 we will restart. Okay, so this is just the kind of replica of CUDA C++ certification that we have seen. Here we are going to write custom CUDA kernels, and that you already learned, right? And here the presentations are also similar, only the codes will be different, right? Because we are writing in Python. Refresh it. So syntactically, it will be different. So if you see, the presentations are similar, just like we have it in the C++ one. Okay, so all the presentations are similar. We will try to understand syntactically how we can write custom CUDA kernels. Okay, so here now we have to convert this add kernel, that is a function, into a GPU function. Okay, so first of all, you see here the input size is defined as 4096. Then X array is defined of type integer 32, size n, and we created Y array like X, but all are initialized to 1. Then here we are transferring the data to GPU in advance by calling toDevice function. X will be transferred, Y will be transferred, and D out is an array that is created on GPU, and its size will be like X array, DX array. Okay, now we are defining here number of thread blocks equal to 122 and blocks per grid, that is a number of blocks equal to 32, right? Now, after that, we are calling this add kernel function, and syntactically, if you see here in C++, we used to provide that kernel configuration in terms of triple angular brackets, but here we are simply mentioning here in list, right? Number of blocks, common number of threads per block. Okay. Then we are passing dx, dy, dout, right? Explicitly here we are passing dx, dy, and dout. The reason is here we have already transferred the data. Explicit transfer is happened, and kind of x is present on GPU. We refer it as a dx. For y we refer it as dy, and dout is the output where we have to store. Right. Then we used CUDA device synchronize. Same way we are using here CUDA synchronize to ensure that this function completes its execution. Okay. And then if you see inside this add kernel, the difference is with respect to normal Python function is we have to use @CUDA.JIT when you are writing custom CUDA kernels. Okay, so far we have seen many decorators, and there is a possibility that you may get confused with all these type of decorators when to use it, right? So just write it down on paper that when we are going to use JIT, when we are going to use ngit, when we are supposed to use vectorize, when we are supposed to vectorize with the function signature and CUDA device equal to true, when we are going to use CUDA JIT device equal to true, and when we are going to use CUDA.JIT. Okay, so once you write it down, you will get a clear distinction between all these decorators. Okay, when you are writing custom CUDA kernel, we have to use there's a CUDA.JIT decorator. Okay, now these are the three input arguments are there, x, y, and out. And here, if you see, we are calculating global ID. And how we calculated global ID in case of C, C++? ID x equal to thread idx.x plus block idx.x multiplied by block dim.x. Right, this was the syntax in C++. Right, but here you can do that as well. Only thing is that if you want to fetch this variable thread idx.x, we have to use CUDA.thread idx.x, then CUDA.thread block idx.x multiplied by CUDA.block dim.x. Okay, so you can write this also, but in Python version, you can skip that manual writing this formula, and you can simply mention CUDA.grid, and in bracket you pass it 1. Okay, see, this is exactly same like this statement. Okay, so it is the short form of this entire formula, and if you pass this CUDA.grid1, it will calculate global ID for all the threads. And simply once you get the global ID, you will do out of idx equal to x of idx plus y of idx. Okay, I'll explain what is the significance of 1 here in the upcoming topics, but as of now, just assume that here, if you pass 1, it will create the global ID for the thread. Right, so here if you observe, it is just only syntactical differences are there, nothing is changed. Okay, so if you know the CUDA programming that we have learned from the previous yesterday's session, then here only the difference is we have changed the syntax. The major difference here is we have performed the data transfer manually. Okay, unlike in C, C++, it was happening automatically. Here we performed it manually. That's it. Rest of the thing is exactly same as the previously discussed. Only difference is syntax. Okay. Hope you are getting it. So I'll give you a few minutes to just go through this syntax, try to get familiar with how we are calculating IDs and how threads and block configurations are defined, how we are passing it. So get familiar with that, and then we'll go to the next part. Okay, there is an exercise that we'll try to solve. Charita, I'm not sure what is the error. No error at my page, but also it is showing failed. Okay, now hope you try to copy the program as it is, because I think I clubbed all things together. There should not be any problem, but still try to modify or the copy paste the code at appropriate position only. Okay, so message by message you copy in the relevant sections. On previous 64. Okay, I think I answered that. Okay. Yes, any doubt? Sangu Venkata Guru, any doubt? Okay, fine. Just let me know once you are done. I will quickly tell you how to solve this assignment, and then we will have a lunch break. Rahul, as I mentioned, it is obvious that as you are attending this CUDA programming session for the first time, you may get confused with those decorators. So what I mentioned, you take paper from chapter 1 to chapter 2, just understand when you are using those decorator. For example, JIT we used only to optimize CPU code. NJIT we used to get error. Then Vectorize we used to optimize code on CPU side, provided that you have universal functions. Then we use Vectorize with type signature, function signature plus target equal to CUDA in order to parallelize the function on GPU side, provided that universal functions are there. And finally, we are using this CUDA.JIT decorator when you don't have, may not have a vectorizable or the universal functions. Some different types of computations are there where you want to manually write CUDA custom kernels. Then we use this decorator. Okay, so you just note it down once and then quickly recap. You will get to know that the difference is clear. Fine. So now moving further, there is an exercise, accelerate CPU function as a custom CUDA kernel. Okay. So what we have to do, this is the function given to us, right? And we want to parallelize it. Okay. So what we'll do first, we'll start with the data. Okay. They are saying here, leave the values in cell fixed to exercise. Okay. We'll keep it as it is. Then we have to perform the operation a square. That means every element of a will be doubled. Squared. Okay. Now here, this is the first to do make. We have to create DA as device array. And how we can create device array? Using this syntax. Okay. CUDA to device. Okay. So we will transfer CUDA to device A array using CUDA to device function, and this will transfer. And the D out, we are going to make D out array. We will initialize like dx. Okay. Not like once. I think just like once, like zeros function will be there. Where is it? Like array like np dot once like will make CUDA device like DA. And it is going to be DA. Okay. Then here we want to update blocks and threads. So we will do one thing. We will launch 4 blocks. Sorry, 104096 elements are there. We will launch 4 blocks here and 1024 threads. Okay, we can take any other configuration as well. Then square device is a GPU function. We will pass here blocks comma threads. Okay. And this function is not going to return anything. So we will mention here out equal to, we'll pass here D out. So comma D out we will pass here. We don't need to mention it here now. And that's it. This is the function call. And here we have to make changes now. Okay. So we'll create ID X variable, and that is going to be CUDA.grid 1. Okay. So this we will take. And what we have to mention here, it is getting out also. Return statement you have to remove because it is not going to return anything now. Out of idx equal to a of idx multiplied by a of idx. Right? So this is what we have to make change. So execute this one now. Hopefully there is not going to be error. Not subscriptable. I made some mistake. Function is not subscriptable. Semicolon is missing. Is there a semicolon in Python required? No, I think semicolon is not required. Oh, major mistake. We forgot to mention CUDA C itself. Okay, so okay, yes. So it is not throwing any error, means it is successfully executing. Okay, so this is how you write custom CUDA kernels. And now in next chapter, what we'll do, we will again do the same thing like what we did in the thread and mismatch grid striding of the loop that we have studied. That we'll try to investigate. And one more important thing here we are going to learn is atomic operations and race conditions. Okay, and based on that we have one assessment. Okay, so we will stop here for this session and we will resume the session at 1. Yashwardhan, could you please be specific which part you want me to explain? Square device function. Okay, so this is the function you want to convert a custom CUDA kernel, right? So first of all, you have to use this decorator and this idx, right? This is how this is the variable that is created for every thread, and this is going to return its global ID. If you recall from CUDA C++, we use this formula, right? Thread idx.x plus block idx.x multiplied by block dim.x. Either you copy this as it is and make it idx equal to this value, but in Python we have short function for that will automatically calculate this, and this is nothing but CUDA.grid1. So that I mentioned here. Now for all the threads we have created global ID, and how we will do that now? Out of idx equal to a of idx multiplied by a of idx. Ultimately we have to square it, a square, right? That means every element of array will be squared. Okay, so now d out is there, the variable. Look, this is GPU function, right? That is called by CPU. So if it is returning any value, so it will be transferred to CPU. Okay, but whenever you write custom kernels, whether it is in C++ or in Python, the functions are not supposed to return any value because there is nobody here to catch that output value, and we have to explicitly store it into the output variable that we have created on the GPU side. Okay, so writing custom kernels, we don't transfer automatically, we have to do it manually. For example, now output variable is updated here, and if you need that back, then what we'll do, you will make d underscore out and then copy to host. This function you have to call, and that you have to store into the some other variable, let's say var. Okay, so by default we don't get return value in explicit kernel. Also we need to keep it on GPU. Whenever it is required, we can fetch it back. Okay, fine. Then we will take here 1 hour break. We will join at 2 p.m. Okay, recording. Okay, so in this exercise we will be having number of threads less than number of elements to process on. Okay, so again the same kernel is there, add kernel, but input size is 100,000 and number of threads will be approximately 3000, right? So number of blocks are sorry, threads per block are 128 and blocks are 30. So 30 into 128, approximately 3000 you will get those threads. Okay, now if you have less number of threads, we have seen the concept of stride, where we can first 3000 threads will work on the 3000 elements. Later on, they will increase their jump size by the stride. Okay, so the stride we can calculate using the formula block dim.x multiplied by grid dim.x. But here we can find that simply by using CUDA.grid size in bracket 1. Okay, so this way we are calculating stride here. Either you can use this formula or you can also use the CUDA.grid size. Okay, and only syntactical difference is there. If you recall, we used for loop there. I equal to you can say here start and I less than the size of your array and I plus equal to stride, right? So only thing is that in Python we use different syntax for loop, so that is followed here, and rest of the code is remains same. Okay, so if you see now, it will execute and it will give you the correct answers. Okay, so this was strided. Now they are asking us to write or convert this particular hypot function using the stride one. Okay, so for that solution is already available. I don't want to waste much time on that because we have already understood that. So you can see here simply they're creating global ID and stride size for I is in the range idx to a dot shape and increase by stride size. Okay, so this is how the function will calculate the output value ci. Okay. Now the important part I wanted to cover is atomic operations. Okay, so here this is the new topic and this is important in order to complete the final assignment from this chapter. Okay, so for that let's try to understand what do you mean by, first of all, race conditions. Okay, so here let's take a simple scenario. Let's say we have a variable and we'll consider that variable, let's say x equal to let's say 5. Okay, now what happens if that variable is shared between all the threads, or that array is shared between all the threads? Now what happens if we are having multiple threads and if all threads are trying to manipulate that value? Okay, so some threads are trying to perform write, some threads are trying to perform, let's say, read. Then problem happens that is called as data inconsistency, right? Data inconsistency means it depends whatever is the final value of x depends on whichever thread execute at the last. Okay, and every time you execute this value, you may get different because final value of this x depends on whichever thread is writing at the last. Okay, now problem is that if let's say you have multiple threads, all the threads are trying to update at the same time, this situation is called as race condition. So every thread is trying to race to update that value. Okay, now though it looks like x, let's say thread 1 is trying to make update one value, right? One thread is trying to increase the value and other thread is trying to decrease the value, right? Now what happens here at the end, what you want, whatever value of x equal to 5 is there, no matter which thread execute, right? Ultimately the final answer will be x value will be same, because if this thread, let's say T0 execute first, it will get increment by 1, it becomes 6. And if this thread execute next, then it becomes 5. Okay. Now, if this T1 thread execute first, it becomes 4. And if T0 execute next, it becomes 5. So ultimately, last value is supposed to be 5. Okay. But though it looks simple that no matter how which thread execute first or last, ultimately value is 5. But at hardware level, this is not the scenario. Okay. What happens at the hardware level? First of all, the value will be read into the register. Okay, so R stand for register. Suppose R equal to, let's say, X, whatever X value is there, 5. Okay, then value is incremented in register. Okay, it is not in the memory but register. And finally, value will be stored into the memory. So this is your main memory from which you are storing the value into register. The increment is happening at the CPU register, and then data is getting stored into the main memory again. Okay, these are the steps happening at the back end when a thread try to perform x plus 1. Same, if thread try to perform x minus 1, it becomes first read the value of x, store into the local register, then it will decrement the value of in the register, and finally store the value into register. Sorry, in the x variable. Okay, now this is the scenario, and if problem occurs when you try to change the order of this execution. Okay, for example, this is thread 0 and this is thread 1. Okay, so this is thread 0 and this is thread 1. Now, if let's say initial value of x is 5, x equal to 5. Okay, now let's say thread 0 reads the value r equal to 5, right? And thread 0 increments its value r equal to r plus 1. Note that as of now, x value is 5 only, right? So r becomes here 6, but that is in register, not updated in the main memory x. Okay, so let's assume thread 0 executed till this point. Now thread 1 also comes and it is also trying to decrease the value of x, and it also read the value of x equal to 5, because x, both of them read the value of x equal to 5, and this becomes r equal to r minus 1, and it becomes 4. Right? Now problem, what has happened here? Both the threads read the value of x equal to 5 in their local register, and updation is happened in their local register. Now this thread 0 trying to update x value equal to 6, right? So x becomes 6 now by thread 0. And at the same time, after this, thread 1 will update the value of x equal to 4, because it read value of x equal to 5 earlier, decreased, and finally it is updated as 4. So x value finally becomes 4, and that is completely wrong, right? Because what we want, thread 0 is incrementing and thread 1 is decrementing, so final value is supposed to be 5 itself. But what problem occurred here? Both of the threads read initial value equal to 5 because they are running in parallel. Okay, so if they are running in parallel, they can read the value of x at the same time, right? And they'll update their local value in the register and then finally save it. And let's assume thread 1 completes the write at the last, then x value becomes 4. And if let's say the final updation is done by thread 0, then becomes value 6, right? And many times if you execute, you will get answer sometimes 4, sometimes 6. So it is not fixed. And that's why the problem is called as data inconsistency. Okay, and this problem is also referred as race conditions. Okay, now these type of situations frequently occur in parallel computing, and to avoid these type of situations or this type of data inconsistency, we make use of atomic operations. Okay, so what do you mean by atomic operation? So atomic means when thread 0 is performing this updation, thread 1 is not allowed to read the value. Okay, once thread 0 completes all the 3 operations, then only thread 1 can perform the operations. right? And if thread 1 is, let's say, performing operations, thread 1 is not allowed, thread 0 is not allowed to read any value that is thread 1 is performing. Okay, so this will how this will ensure that correct output. So let's say thread 0 first executing this resetment. So it read the value of x into register. Okay, then incremented the value of x into register. Let's say it becomes 6. And at the same time, let's say T1 tried to access the value of x. Right. At that time, this atomic operation won't allow thread 1 to read the value of x. So it will tell that, okay, you have to wait till thread 0 completes its operation. Now thread 0 completes its operation, the value of x becomes 6. Now only after thread 0 completes its execution, thread 1 is allowed to go and perform the operation. Now thread 0 is completed, thread 1 will go. It will read the value of x as 6 now because the value is updated to 6 by thread 0. Then it is decrementing by 1, it becomes 5 and final value becomes 5. So it becomes 5. Okay, the same thing with the thread 1 is executing first, right? So let's say thread 1 is executing first, so value becomes 5 here, right? This value is 5. Then the r equal to r minus 1, it becomes 4. And let's say in meantime, thread 0 is trying to access the value of x, then it will not allow thread 0 to read the value of x. Thread 0 has to wait till final operation of T1 is completed. So final operation of T1 becomes it 4, and then thread 0 will execute. It read the value of x is 4, it makes it 5, and final value becomes 5 again. Okay, so this is called as atomic. The name atomic indicates that you execute all your instructions or none. Right? If you get chance to execute, you execute all these 3 instructions, or you are not allowed to execute any instruction. Okay, and why any thread is performing this kind of atomic operation, no other thread is allowed to read or write the values. Okay, so that is called as race condition, and this is how using atomic we can take care of those race conditions. Fine. Now you can see here, this is the example where the race conditions are demonstrated. So first function is thread counter race condition. That means here race conditions will occur, and the second one is without race conditions. So first what we'll do, we'll try to understand what this function is trying to do. Okay, so thread counter race condition, it is taking global counter array as an input. Okay, and here when we are calling thread counter race condition, we are passing 64 blocks and 64 threads. So all threads will perform increment on global counter 0th location. Right, so all threads are trying to perform the write or increment the thread 0 value. So let's execute and we'll see what happens. Okay, so it is expected that if number of threads are 4096, after final execution, we are expecting that the value of this global counter at 0 will be 4096, because 4096 threads are trying to update this value. Okay, but what we are getting here, output as 1. Right, the reason could be the thread 1 is updating at the last. Okay, so if I execute again, we are getting wrong result. Right, but now here the same global counter variable array and its location 0 is getting incremented by 1, but using CUDA atomic add. Right, so what is this function? CUDA atomic add. First we have to pass here the address on which the atomicity you have to apply, the location, right, and the amount by which you want to increment that value. Okay, so this atomic add function ensures that each thread will get its chance to execute this addition, and while that addition is happening, no other thread is allowed to perform read or write. Okay, so let's see what happens when you execute the correct version. So you can see here output we are getting is 4096. Right, so that's the difference between atomic operations. Okay, fine. So you read this carefully and execute these cells and try to see the output. Meanwhile, if you have any questions, drop in chat box. Very nice observation, Yashwardhan. Okay, I was about to ask that question. What is the drawback of this atomic operation? You correctly pointed it out. Okay, so the drawback of this atomic, if you see, it is making the program or this updation sequential, right? Because only one thread at a time is allowed to global counter 0. Okay, thread 0 will come, maybe let's say thread 100 will come, then thread let's say 150 will come, but all threads are executing parallel, but only one thread is allowed to update that location at a time. So obviously we are creating 4096 threads, but only one thread is allowed to update at a time. So it becomes sequential. Okay, so that is the limitation or drawback of this atomic add. But there are some situations where you cannot avoid these atomic operations. Okay, so in parallel computing, typically we try to avoid these atomic operations in the your algorithm or race conditions in your algorithm by making change in the data structure or by making change in your algorithm. But sometimes it is not avoidable, right? So in that case, we have to use this atomic add. Okay. Okay, try it. And once you are done, let me know. Okay, so I guess it won't take much time to understand that code. So let's move on to the final assessment. And here, let me guide you through the assignment. So we have here histogram kernel. Okay, so I guess all of you are familiar with what is histogram. So basically histogram means we have given set of numbers, right? So we will be having numbers, right? Array, and we will be given some bins, right? So some bins, and that those bins are having some ranges, right? So let's say we are trying to calculate histogram of people height. Okay, so we'll be having, let's say, 130 centimeter to 140, then 140 to 150. Okay, then 150 to 160. Likewise, the range of the height will be there, and based on the number of, let's say we are having 1 million people, and their height will be stored here. Okay, so 176, right, 139, likewise 152, likewise height will be stored, and we have to drop in their appropriate buckets. So if 176 is there, we'll drop it here. 139 is there, we will drop it here. Then 152 will be dropped here, and likewise we'll be having 1 million entries. Those will be dropped in their respective buckets, right? Now if you want to parallelize this operation, what happens? Race conditions will occur, right? For example, I'm also having here 151, and let's say this is getting handled by thread 3 and this is by thread 4. So these two threads will try to update at the same memory location in these bins. Okay, so we will increase the bin count by 1 here. Okay, so if we have 2 elements here, so the value of that bin will be 2. Okay, if in this case 139 is placed here, so we will add 1 to that location. Now, two threads are trying to update at the same memory location, then problem of race condition will occur here. Okay, and to resolve that race condition, we have to take care of atomic operations. Okay, now let's try to understand here. CPU version of your histogram is given, but before that, let's see what is the input here. X is the input, right, which is having 10,000 elements. X minimum and X max are the values -4 to 4, and histogram output will be there of size 10, which is initialized to 0 using NP zeros, and CPU histogram function is getting called X, X minimum, X max, and histogram out is the output array where you have to increase the bin counter. Okay, now here in this function we will be having number of bins, and we will get that by histogram out dot shape. So its size is 10. Okay, so that is nothing but the number of bins, and bin width is nothing but X max minus X min divided by number of bins. Okay, that is going to be the width of the bin. Okay, so every bin is of equal size here. Now here for every element in X, right? So for every element in this X, what we are going to find out its bin number first, right? So how we are going to find out that element? Subtract minimum value from that and divided by bin width and convert this into integer. It will give you in which bin number you have to place it. Okay, and if the bin number is greater than 0 and bin number is less than histogram output that shape, then only we are going to perform this increment. Okay, so if this is the condition, just to discard the bin numbers which are less than 0 and the greater than that output array size. Okay, so in that case, if you see here, histogram out bin number plus equal to 1. Okay, so now it is possible that if you try to execute by multiple threads, many threads will get the same bin because the values are initialized randomly. Okay, and from the normal distribution we are taking. So if multiple threads are getting the same bin number, then race condition will occur while updating this histogram out. Okay, so then you will get the data inconsistency. Okay, so now our job is to convert this sequential implementation into parallel, right? And we will call it as a CUDA histogram. Okay, in your notebook implementation, CUDA implementation is not given. There is a blank space given here, but I try to write that function now, and this is the solution. Okay, And the one thing is different here in this chapter, you don't have to directly go for the assessment here. Rather, you have to copy paste whatever solution is there into that histogram.py. If you click on that, it will open histogram.py. Okay. So first of all, you have to convert this CUDA histogram, right into that parallel version here. Okay. And then you have to uh, copy paste. If you are getting correct output, then you have to copy paste the code into this histogram.py. Okay. So let's see what is the parallelization strategy would be here. So we will be having a start that is going to be a global ID. Then we will create a stride here. Okay. And its size will be CUDA.grid size 1. So this is the, just like we are creating global ID and stride here. Okay. Now this is also same. Number of bins, it is same, and bin width is also same. So till this point, there is no change. Okay, because this is just an initialization. Now we are going to create threads. Can you tell me on what basis you are going to create number of threads? How many threads you will create here? Or which parameter here will decide number of threads? Based on which parameter? No, not number of bin. Exactly. Deepika, you're right. So X array, which is of size 10,000, right? So we will create 10,000 array threads, right? And all those 10,000 threads will find out their corresponding bin in which they want to place. Okay. So here, if you see, we have created for I in the range star to X dot shape and stride. So this is your strided loop. Okay. And inside this bin number, if you see what we are calculating, we are taking X of I, that corresponding ID or the element. We are subtracting it and divided by bin width. Okay. For every thread, we will calculate this. Okay. Just like here, we calculated bin number. Okay. Now, once you get the bin number, here we are making major change. Here, where the race condition was there. So we will make CUDA atomic add histogram out bin number and 1. Okay. So you need to remove this pass. Okay. So now you can see here, this is our parallel implementation. So let's execute this and see. Okay, it is giving error. Mismatch is 100%. Let's see where I made mistake. Bin number, and we are adding 1. There should not be any error. What is the output? It is getting X is 0. Where we are updating. Let me execute first previous cells. Okay. Yeah. So sometimes if you don't execute the previous cells, then you may get error. So now I executed the previous cells, and now it is giving the correct answer. Okay. So this is how you parallelize this CUDA histogram. And you can see now you have to exactly copy paste this code and you have to place it in here. Okay. Save it. Then you have to go back and you have to click on assess task. Right. So this is the code that you have to modify. Rest of the things you have to keep it as it is. Fine. So try it. If you are facing any problem, then let me know. For your reference, you can have this code with you. Okay, note that this is a Python. How start? Look, let me clear that one thing before. This is a Python code, so indentation is important. So when you are copying it, if the indentation is wrong, you will get the error. Okay, so the space is supposed to be just like here. Okay, coming to the point, the question was how start and stride is working here. Okay, so to understand that, let's take the x size is, let's say 10. Okay, so we will be having 10 threads: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the correct situation or the optimal situation where we will be having 10 input size and 10 threads. Then this stride concept is not required because we have enough threads, right? So 10 elements are there in X. So every thread will take that corresponding element. It will try to directly, this for loop is also not required in that case. So every thread will go corresponding that X element, they will read, and they will find out appropriate bin number, and atomic operation will be performed, right? But now here, if you observe, what is the size of X? Size of X is it is defined 10,000. Okay, size of X is 10,000. And how many threads and blocks we are launching here? 2 to the power 7, 2 to the power 6, 7, 13, 8,000, right? Approximately 8192. Am I right? 2 to the power 7 into 2 to the power 6, 2 to the power 13. So it is going to be 8192. Okay, and how many elements you have? 10,000. Okay, so some elements will be remain, right? So we are having less number of threads. So in that case, we have to make use of this stride again, because to work on the remaining elements, the first 8192 threads will again increase their stride or the ID by the stride, and they'll work on the next element. Okay, so this is how the striding concept is used here also. Note that first of all, you need to get successful message, or there is no message here. If your submission is wrong here, code is wrong, then you will get assertion error here. If you are not getting any output here, that means your code is running correct. Then you have to copy paste this code and you have to paste it here, then save it, then go back and click on assess task. Okay, so the steps are a bit different here. Fine. How many of you able to complete? Just quickly raise your hand. Great. Okay, function. Okay, make sure you have all executed these import statements for CUDA and all as mentioned by somebody else. Okay, don't directly try to run these cells. Okay, so you can stop the task now, those who have completed. Do you want some time to work on that assignment, or shall we move to the last chapter? If required, we can take. Okay, just let me know what is the error that you are facing. Or if possible, I will allow you to share the screen. Yes, Yashwardhan, do you want to share your screen? Deepika,
Yeah, sir.
anybody? Yeah, please
Yes,
share.
I'm sharing.
Okay, 1 second, I will give you access. Oh, you can share it now. Okay,
Is it
please
visible,
scroll
sir?
up.
Yeah.
Yes. Please scroll up.
In these two cells, I'm getting the error.
Please scroll up. Let me see the code.
Mhm.
Atomic histogram type error assertion function object histogram. Okay, D histogram out. Shape is fine. Okay, next. If pin number equal to greater than 0 less than shape atomic error. Okay. Do one thing, you execute all the previous cells. Just scroll up.
Mhm.
Execute the previous cells in
From here?
sequence first. Yeah. Yes, from line number 20. No, not 20. Scroll a little bit down.
From here, no,
Yes.
sir? Put on dot jet.
Yes.
This one.
Yes. Go on executing all the cells below that. Let me see. Is there anything missing in your? Just go on executing. Execute. Go. Execute. Okay. Assessment. Go on. Execute. Go down.
Still,
Go
it
down.
is showing the same error.
In CUDA histogram, you missed that CUDA JIT, right? Decorator itself is missed.
Okay, so
At the rate CUDA.JIT.
here in this one.
Yes,
Yeah.
above this CUDA histogram definition function is there, right? At the rate CUDA.JIT. Save it. Now go on executing those cells.
Okay. Spelling is yes. Yeah, it's gone now. Yeah, thank you.
Execute now. Next.
Yeah, it's working. It's working.
Okay. Fine. Now copy paste
you.
that CUDA histogram into that histogram.py. Just scroll up.
Yeah, I'll do that. Thank you, sir.
Okay, fine.
Thank
Yes,
you.
Yashwardhan. Still you have error CUDA JIT. Yeah, Nihal, I think you pointed out correctly. Yashwa, then what is the error? Okay. Okay, scroll up. What is error? Scroll a little bit up. Scroll down in that. Let me see what is final error. Typing error. Scroll down. Int 32. CUDA to device histogram. Okay, go to that pin number. Let me give the CUDA histogram. Okay, I think you remove those lines, max minus min bin width and what was that line? Number of bins, you have to ensure that it is of shape, histogram, out. Yeah, these two lines. N bins equal to and bin width equal to. You have not mentioned those two lines there. Mention it, it will work. Okay, those who have completed, go to the third chapter and click on start button. As it will take few minutes to launch that cloud instance. Go to third chapter and click on start button.
This error is still coming.
Okay, let me see. Oh, okay, this is CPU histogram. Go up. I'm not able to see your code, only error is visible. Just scroll up. Scroll up, show me the CUDA histogram function definition. Yashar, I'm not able to. So element in. No. You need to take X of element, I guess. Right. So you have to change that to index for I in range. Okay, because start you got the ID. Remove that for element that you have mentioned. Mention it as I, and then you have to read X of I. Right. In the next line, bin number equal to element minus x min is there. So remove that element and make it x of I. Now you will read that corresponding element by the thread. In earlier case, there was only a single process, so you read in the for loop that element, but now you cannot do that. Okay, yes. Now check. Let me see, is there any other? Check it once.
Yes, sir, it's now working. Thank you.
Yeah. Fine then. Open that third chapter now. Again, Harkun core, perhaps you are making some mistake in the code itself. If you want, you can share your screen. We will try to figure it out. Meanwhile, our session will load. I made you co-host. If you want, you can share the screen. Harkun, are you going to share your screen or shall we move on? Okay. So this is the last chapter. I'll just give you overview of this chapter. You can complete the remaining exercises later. So The most important topic here is uncoalesced memory access hurts the performance. Sorry. So basically, in this chapter, all the advanced CUDA topics will be covered. Okay. So far, whatever you have learned in CUDA C, C++, and CUDA Python, those are fundamentals. Okay. In this chapter, some advanced concepts are there where you will not only get the performance just by parallelization or dividing the task among threads, but you need to also take care of things like memories, different memories present in the GPU and how effectively you have to use it. Okay, so the first thing is whatever data you transferred on GPU, that will be placed into GPU's main memory, right? And that main memory is referred as global memory. Okay, so only the name is different, new here. So whatever data we used to transfer from CPU to GPU using that to device function, okay, so that used to be placed into the GPU's RAM, and we mentioned earlier it as a DRAM, but in CUDA context it is mainly referred as global memory. Why global memory? Because this memory is accessible to all the streaming multiprocessors, right? So we have seen in the yesterday's session that there are streaming multiprocessors are there. Okay, so all the streaming multiprocessors have access to that RAM. So that's why it is referred as global memory. Okay, now in order to get a better performance, we have to access that memory properly, right? Because if you have some randomized access, then you may not get the better performance. Okay, to understand this concept, we have a topic that is coalesced and uncoalesced memory access. Okay, so we'll try to understand that coalesced and uncoalesced memory access. Okay, for that here they have created input arrays and some data they have initialized with. So here we are having input size 1024 by 1024, that is 1 million. Okay, threads per block we have 1024, and number of blocks equal to n by threads per block. Okay, so we will get 1024 number of blocks here, and there is a stride here that is defined. This stride is different than what we have decided earlier. Okay, don't get confused with, I'm not sure why they included the same name here, stride, because just it is could be the just it is the size is getting by multiplied by stride, they have used it, but don't get confused with the stride that we used earlier. So it is nothing but we are going to create an array A of size stride by n, that is 16 million elements will be there in the array A. Okay, and B will be copy of array A, right? Now we have output vector which is initialized to 0. We will transfer this A array to GPU by using to device function, B array to GPU by using device function. Okay, and the same way D out is also transferred. Okay, so far nothing fancy. We simply initialize the arrays, right, and we transfer the data to GPU. Now, to understand the concept of coalesced or uncoalesced memory access, they created one add experiment function, right? That is a GPU function. You can see this decorator CUDA.jet, and here we created array, global ID and stored into this I. Okay. Now, if it is coalesced equal to true, then we are performing A of I equal to A of I plus B of I. Okay, so if we have thread 0, then it is performing A of 0 plus B of 0 plus B of 0. If it is thread number, let's say 1, then it is performing A of 1 plus B of 1. Okay, and so on. This is the pattern you will observe in all the threads if coalesced equal to true. Okay, but if coalesced is not equal to true, then how this addition is getting performed? A of 0 multiplied by thread 0 is there, so stride is 16. So A of 0 plus B of 0 for thread 0, right? But thread number 1, it is updating A of 16 plus B of 16, right? Similarly, thread 2 will perform A of 32 plus B of 32. Okay, so if you see the difference clearly here is, in first case, if data is getting accessed or the flag coalesced equal to true, then nearby threads are accessing nearby elements, right? Thread 0 is accessing A0, thread 1 is accessing A1, thread 2 will be accessing A2, right? Same way, thread 0 is accessing B0, thread 1 will access B1, and thread 2 will access B2. So all these nearby threads accessing the contiguous data, right? And if the threads are accessing this contiguous data, we call it as a coalesced memory access. Okay. Now, in second case, what is happening? Thread 0 is accessing A0, but thread 1 is accessing A16. So there is a gap of 16 elements between A0 and A16. Right? Same way, B0, B16. After that, they are accessing A16 and A32. Thread 2 is accessing A32. Note that all these are trying to run in parallel at the same time. Okay. But if they are accessing the data which is far away from all the threads, then it is called as uncoalesced memory access. And that access hurts the performance. Why? Because the thread is accessing A0 that is stored in the global memory. And when thread 0 access the A0, global memory is not going to return only that element. It is going to return some chunk, nearby chunk. Okay. So let's say this is your A array, right? And thread 0 is accessing A0. Okay. And let's suppose somewhere here A0 is there. Okay. So when thread 0 access the data, it is not going to return only A0, rather than it is going to return some chunk, right? And perhaps you can noted this out that this is the behavior of your cache memory, right? So when you access data from main memory, it is not going to return only that data, but rather than it is going to give some chunk of data that will be stored in the cache memory. And in future, if the data is required, that will be fetched from the cache memory. Okay. So in this case, if thread 0 is requesting this data, right, thread 1 don't have to make a request for another memory transaction. Rather, once 0, 1, 2, 3 elements are available in cache, then thread 1 will also get the data from the cache itself. Right. So thread 1 has not have to go and make another memory access. This will save memory access time. Unlike here, in case of uncoalesced, once thread 0 is accessing A0, the memory will return these 4 values, suppose, but these 4 values are not required for by this thread 1. Thread 1 will require completely new data A16. Now somewhere from A16, this chunk will be loaded and will be provided to thread 1. Thread 2 is not even requiring the data from this range. Somewhere from this range, thread 2 is requiring. So in second case, more memory transactions will be performed, whereas in first case, less memory transactions will be performed. And that's why it will improve the performance if you have access in coalesced fashion. Okay, so let's see whether it is our hypothesis is correct or not. So I'll execute when the flag is to coalesced flag equal to true. It is giving you 226 microseconds, and let's make it false and we'll see how much it is taking. So it was earlier taking 226 microseconds, but now you can see it is already taking too much of time. It is taking more than usual. Yes, so you can see here it is taking 540 microseconds. Okay, earlier it was taking 220. Approximately 3 times performance improved if you have the access in coalesced fashion. Okay, so that is the one thing. Fine. So here is the presentation for coalesced memory access. You can explore it later. Now I'll give you brief idea about important thing is is 2D and 3-dimensional grid box. Okay, so yes, sir, then don't get confused with that stride. Okay, the previously what the stride word we used is to increase the jump size for every thread, right? Here we are not using that striding concept, rather than to demonstrate only that threads are accessing data which is placed at the distance of stride. Okay, that is demonstrated here. We are not creating any that stride here. Okay, stride is used only to give access to that array at the stride distance apart. Okay, we are not incrementing thread by the stride value here. Okay, that's why I was telling earlier that don't get confused with that stride we used earlier and here. Here you just need to accept that if nearby threads are accessing nearby data, right? Maybe A0 it is accessing and thread next is accessing A1, it is good for performance. If thread 0 is accessing, let's say A0, and next thread 1 is accessing, let's say A100, then it is not good for performance because 2 memory transactions you have to make. Fine. Okay. Now coming to the part here, 2-dimensional and 3-dimensional blocks and grids. Okay. So far, we have seen that we created the blocks and the threads within the block in 1-dimensional fashion. I've just mentioned that we have one block and which is having threads. Okay, like this. So this is block 0, thread 0, 1, 2, 3. This is block 1, thread 0, 1, 2, 3. Okay, 0, 1, 2, 3. Right. In this case, you can see the threads and blocks are organized in only one dimension, that is X. And if you recall, we used to say thread IDX dot X, and dot X was nothing but this X dimension, right? So far we use only one dimension organization of threads within the block as well as the blocks in the grid. But now we can organize these threads and blocks in 2 dimension as well as in 3 dimension. Okay, and the reason is sometimes we will be having data which is not in 1 dimensional but in 2 dimension. For example, you are working on matrices. Okay, matrix is having data arranged in 2 dimension, m rows and n columns, right? So in that case, we either can use 1D thread and block structure, right? And we can assign every thread to work on these all elements, or we can organize threads in 2 dimension, right? So number of threads in X direction and n number of threads in Y direction. Okay, sorry, I think I made the reverse one. M number of threads in X direction and n number of threads in Y direction, right? So why this is useful? Because when you're working on 2-dimensional data, it is easy to map the threads if they are organized in 2 dimension, right? Same way, if let's say your data is in 3 dimension, so most likely when you are working in the fluid dynamics or the 3-dimensional simulations, so your data is stored in the 3 dimension or the 3D array. In that case, if you organize your threads in 3 dimension, then you will get the mapping of thread to the data point easily, right? Rather than creating only one-dimensional threads and blocks. Okay, so we'll try to understand this with this example of I think matrix addition program is there. Let me see, is there presentation for that? No. Fine. So you can see here now I'm having array of size 4 cross 4, right? Earlier we used to work on only one dimensional array, but now here array is 2 dimensional. We transfer this array to device, that is GPU, and now you can say here the number of blocks is 2, 2, right? So earlier we used to say that number of blocks equal to n divided by threads per block likewise. But here number of blocks are 2 in x direction and 2 in y direction. So what do you mean by that? I'll be having this block, 2 blocks in x direction and 2 blocks in y direction. Okay. Now threads per block also in 2 dimension, 2 in x, 2 in y. So I'll be having this thread 2 in x direction, 2 in y direction, 2 in x direction, 2 in y direction, likewise. Now you may ask, this is the logical diagram, how it will affect in our thread applied to the corresponding data. Note that we have array of size 4 cross 4, right? So it is having 4 elements, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, now what happens? This block, right, or the threads of this block are responsible to perform operation on these elements. Okay, so I'll just use some color coding here. Okay, so this is the block or these which contains 4 threads. These 4 threads will work on these 4 elements. Okay, same way these 4 elements, 4 threads will work on these 4 elements. Right. So logically, if you see here, it is quite easy for us to understand also and to apply these threads to the data points also. And finally, if you see here, these are the 4 threads will be applied to these 4 elements. Okay. Now, question is how we can map this. Okay. So the way we said that the threads have their local IDs in X direction, same way they'll be having local IDs in Y direction. Okay. So this is your X direction and this is your Y direction. Okay. So this thread is having now 2 IDs. Thread 0 in X direction, 0 in Y direction. This is thread 1 in X direction, 0 in Y direction. This is thread 0 in X direction, 1 in Y direction. This is thread 1 in X direction, 1 in Y direction. Right? Same way, 0, 0, 1, 0, 0, 1, 1, 1. 0, 0, 1, 0, 0, 1, 1, 1. Here 0, 0, 1, 0, 0, 1, and 1, 1. Okay. Right. So this is how the threads are organized in 2 dimensions. Now, what we have to do, we have to map these to the corresponding element, right? But these are the local thread IDs, 0, 1, 0, 1. These are the local thread IDs. We have to calculate global ID, right? And we know how to calculate global ID using this CUDA block dim.x multiply by dim.x and thread ID x.x. Okay, so this will give you global ID in X direction, and we need to calculate global ID in Y direction as well. So that will be calculated by using dot Y. So you can see here new axis we added here dot Y. Okay, and now based on that we will get this thread. If you find get the global ID will be like this. So 0, 1, 0, 2, 0, 3, 0, 4. Okay, so this is your global X ID. Okay, I think I made a mistake. So this will be 0, 0, 1, 0, 2, 0, and 3, 0. Okay, in X direction, the global ID is changing. Same way we'll get 0, 0 here, 0, 1 this thread, 0, 2 this thread, and 0, 2, 3. Okay, this become 1, 1, this become 2, 1, this become 3, 1. This become 1, sorry, 2, 0, 2, 1, 2, 2, 2, and 3, 2. And this becomes 1, 3, 2, 3, and 3, 3. Right. Now, if you see, when you get the global IDs, right? So this 2, 1 thread, its global ID is 2, Y global ID is 1. Okay. So it will go 2, 1, right? So on corresponding location, okay, I think it is right. 0, 0, 1, 0, 2, 0, 3, 0, 0, 1, 1, 1, 2, 1, 3, 1, 0, 2. So X is it is correct, but only thing is now when you see, first of all, in X direction we have column, and in Y direction we have row. Okay, so row and columns are interchanged here. So 1, 2 you have to go, right? So I followed an X and Y convention here, but actually we have to follow row and column, right? Typically we have tendency that on X axis, when we say we call it as a row, and Y axis we call it as a column. But if you see, Y is changing in vertical direction, so we have to make it row, because rows are changing in vertical direction and columns are changing in horizontal direction. Okay, so that's why I got the reverse here. Okay, so here 1, 2 means first row and second column will be mapped here, right? 1, 3 means it will be mapped here. So this will be mapped to here, this will be mapped here. Okay, so now once you have this sort of thread organization or layout, then you'll be easily able to apply this number of threads to the corresponding data. Okay, so if you see here now in this example, what they did, they first of all created these two global IDs, X direction and Y direction. Either you can use this formula, or you can simply use this CUDA.grid in bracket 2. Now you can see here 2 indicates 2-dimensional threads we have to create. Right? In earlier case, we used only 1 here. That means it was 1-dimensional. Okay. Now, if you see here, what they are trying to do here, once they create X and Y. Okay. Now here X is nothing but row and Y is nothing but column. Okay. And simply what they are performing, AXY equal to X plus Y by 10. Some dummy computation they are performing. Okay, and rest of the things are going to be the same here. Calling the function, and we have to pass blocks, but remember blocks are in 2 dimension, and threads per block is also in 2 dimension. Now, if I ask you, how will you calculate total number of threads? What will be the formula? Rows into columns, that is also fine. But if I ask you in terms of blocks and threads per block, simply what you'll do, you'll calculate total number of blocks. How will you calculate total number of blocks? Blocks in X direction, blocks in Y direction, multiply. It will give you 4. How will you calculate threads within the block? Number of threads in X direction, multiply by number of threads in Y direction, that is 4. So it will be launching 16 threads. And how many elements are there in your array? 4 cross 4 matrix is there, so 16. So 16 threads we launched here. Okay. So again, this is the first time you are observing these threads and block configuration in higher dimension. It will take some time to digest because it will slightly confusing for you. Okay. So what you can do, always try to draw on paper. Okay. This is my matrix organization, and this is how my threads are organized. And this is how I'm going to assign the IDs. Right. First of all, assign the local IDs, then try to use this formula to get the global IDs, and then try to visualize which thread is getting mapped based on this an index axis. Okay, so if I execute this, you'll get the correct answer. Fine. Now there is an exercise to demonstrate coalesced matrix addition. Okay, so here you just simply need to go through it. So we are going to create n, that is 4 million elements are there. Threads per block equal to 32 cross 32. That means 1024 threads are there, and we'll be having blocks 64 cross 64. Okay. Then we are creating NumPy array or matrix of size 2048 by 2048. B is also a similar copy, and we are going to create output array. Initialize it to 0. Copy all the arrays A, B, and out to the GPU. Okay, this is just initialization. This is the matrix addition program that you have to change. Okay, so one is a coalesced one and other is the uncoalesced one that you have to modify. Okay, so I'll directly refer to the solution here, and if you'll see, only the index values are interchanged, right? So if it is coalesced access, then y comma x is mentioned, and if it is uncoalesced, x comma y. Why so? Whichever is the fastest changing dimension, you have to mention at the end, right? So you can see here, we change the when we try to read the array, how we read first row and all the columns, then second row all the columns. So x dimension is changing at the fast compared to y, right? So we'll go to the row 0, then go all the elements, then go to the next row, then go all the elements. So fastest changing dimension is x. So if you make here x at the end, then it will be the coalesced, and if you switch that, it will be uncoalesced. Okay, so what happens if it is switched? Then this thread will be accessing this element, this thread will be accessing this element in the like this fashion. So this is going to be uncoalesced. But in coalesced fashion, what we are expecting, this thread is supposed to access this element, this thread is supposed to access this, this has this has this. So this is coalesced one, right? And if you see, the performance difference will be more. Let me copy as it is here. Okay, coalesced versus uncoalesced performance. If you see here, okay, so results are correct. It is taking 203 microseconds for coalesced access, and okay, so it is taking 591 microseconds, right? So almost 3 times performance you will lose if the access is uncoalesced. Just by changing those array indices, you can see 3 times performance you lost here. Okay, so you have to be very careful in that. Fine, so I'll give you a few minutes so that you can go back and you can execute all these cells. Okay, and I'll keep this topic as an assignment to work on shared memory. Okay, very interesting topic is there, and which will indeed help you to improve the performance at next level. Okay, and finally you have one small assessment and only one change you have to make in that assignment. Let me show that. Where it is. Okay, I'll show you that later. Just take 4 or 5 minutes and try to execute all the cells till shared memory. Okay, and see the performance. Are there any questions? How long we can get access to those notebooks? I think um, there is a limit on number of times you can launch that cloud instances. Okay, and I don't know what is the exact number, but just assume that maximum 10 times you can launch every cloud instance. Okay, it happened with me as well, because every time I used to start that cloud instance, and after a few days I used to get message that maximum cloud instance launch limit reached. Okay, then you have to drop mail to the NVIDIA support team, then they will allow you to get access. But I'm not sure whether they will allow for participants. So try to ensure that complete these certifications, okay, as quickly as possible, right? And if you don't have enough time to sit, don't try to launch the cloud instances, okay? Because if you have 1 or 2 hours continuous, you can sit, then only you can launch the cloud instance and work on that. Yeah, you can download these notebooks. That is also fine. Access task second section. I didn't get any error while running my code. Occasion, you can do one thing. You can, if your that cloud instance is live, you can show it to us. We'll see. I'll make you the co-host. Okay. Then the problem could be you are not copying that code correctly in that log, histogram.py. I cannot resolve without looking at the code. Okay, get 2D indices, blocks, there's for block TA getting error. Charita, I'm not sure what type of error you are getting because I don't know your code. So if possible, you can share the screen and show us. Okay, you can work it on. Here, shared memory topic is there. I'll keep it you for an assignment. You'll get to know that very interesting topic it is there. And last assessment is there. Here, only one change you have to make in the entire code. That here you have to make 33. Okay, and if you make there 33, you will complete the assessment. Okay, and once you replace 32 with 33, execute all the cells, right? From imports, data creation, all the things, check performance, run the assessment. Okay, it will give you congratulations message that you have been passed. So that is the only change you have to make. And now once you complete that, go back and click on assess task and it will show the message passed or failed. Okay. And then is it showing you quiz here at the end? Because for me, it is showing one quiz here, but it is supposed to be for me only. I'm not sure whether it is there for you. Can anyone please confirm? Are you able to see any quiz below? You have to, in this line, where tile transports conflict free is there, here you have to mention 33. That's it. That is the only change you have to make. I just highlighted that line. Okay, so I think the quiz was for me only. Okay, so once you complete this, go back and click on assess task, right? And it will give you flag that you have passed. And then you can go to my learning section here and you can verify your certificate here. Okay, how many of you are able to generate the certificate? Quickly raise your hand. Fine, then I think that is the only change you have to make in order to get the certificate. So here size is supposed to be 32 cross 33. Okay. Though I'm saying this solution, but make sure you will go through these topics because of the time limitation. I could not explore that. Okay. So now what is expected from your end from these two certifications? So you generated the certificate, but two topics we left, right? So in CUDA C, C++, we left profiling chapter, and in this Python certification, we left this shared memory. Okay, so now first of all, revise all these topics clearly, get sound and understanding of these topics, right? And then finally, you go and visit those topics, right? Because those topics are bit advanced, right? Not in the context that completely advanced, because advanced CUDA programming is different. Okay, but in order to get the first performance, whatever you have understood so far is enough. Okay, that means if somebody is going to ask you now, this is my program, can you convert into parallel one? So you will be able to do it, definitely. Okay, but next thing is, once you convert your sequential code into parallel code, next step is you need to profile, you need to optimize memory, and you need to keep on doing this till you get the maximum performance, right? So apart from that, there will be a few more advanced concepts will be there. Okay, but assume that you already know now 60 to 70% of CUDA programming, because the main task that you perform when you want to write a parallel program is this, right? Take sequential, understand data transfer, where need to data to be replaced, how many threads to be created, how to assign tasks to different threads. That is the first thing and the most important thing when you write a CUDA program, right? Once you get that performance improvement, then next thing is, by using different tricks and uh, optimization things, you will be able to improve the performance even further. Okay, fine. So with this, I think I can conclude here for CUDA programming certifications. So before we conclude, just raise your hands. How many of you are able to generate the certificate? Okay, great. So fine. Now your CUDA programming track is over, right? So you are in slot 2 and your CUDA programming track is over. Now you will be, we are going to start with the deep learning, right? Tomorrow you will be having deep learning. Followed by that, there will be predictive maintenance course, and then there is going to be transformer based NLP. Okay, so this is comes under the accelerated computing, and the remaining 3 certifications comes in the your artificial intelligence. Okay, so try to complete all these certifications during the same day itself, so that it won't bother you later on, because once we go offline, and we will not be able to resolve your queries effectively on WhatsApp, right? So we need to see the code, we need to check what type of error is getting. Sometimes we have to execute, right? So it is quite tough to debug your errors just by looking at image. Okay, so try to complete that, and for our group purpose, try to publish your certificates, that is achievement, on the LinkedIn, and do tag GPUG Club and NVIDIA, so that it will reach to maximum. And we just want to reach this club to maximum students and faculty, so that they can get the knowledge, right, just free of cost. Okay, and this is also important for us to schedule such kind of events in future as well. Now these are the 5 certificates we have planned, but in future we are going to plan for generative AI, maybe some advanced topics in CUDA. Okay, so that sort of workshop we are also even trying to plan, but we want to reach maximum. And also the thing is that try to attach these certificates in your resume. Try to attach this certificate on LinkedIn profile, right? So this will uh, attract tentative recruiters for you also. Okay, and whenever you are mentioning these certificates in the resume, try to understand all the topics in that, because just you are having certificate, and that doesn't mean that you have knowledge. Okay, so whenever you are mentioning anything in your resume, make sure that you know that technology thoroughly. Okay, so if you are mentioning CUDA And if the, let's say, interviewer is asking you what is the difference between thread and block and grid, and if you're not able to answer it, then there is no use of this certificate. Okay, so if you are mentioning in the resume, make sure to understand all the concepts properly, and then only you keep it there. Okay, fine. So we'll conclude here. If you have any further queries, definitely you can post it in the chat box in WhatsApp. Okay. Yashwardhan, you don't need access code now. Okay, so those courses will be on your profile. Okay, so you can log in to your account and you can open as many times you want. Yes, Keshan, if you want to share the screen, yes, please go ahead.